analog mixed signal session 5B. So I would like to give a brief introduction to our invited speaker, Professor Amit from UIUC. He completed his undergrad and graduate degree from IIT Kanpur in 2008. And he has been a tenure track at UIUC. And in 2021, Amit has been awarded the NFS Career Award for his project on robust and ultra-low power spatial intelligence. Please welcome Professor Amit.
Thank you so much for the introduction. I'll talk about our work on using computed memory, not just for energy efficiency, but also to perform deep learning computations which are uncertainty aware, and they can be significantly robust compared to traditional models. So applications of deep learning have been evolving over the past couple of years. These days you can take your phone, you can take a photo of the food that you are eating, it can tell you how much calories you are consuming. And you can use deep learning to analyze healthcare images, CT scans better than a doctor could. These days you can also use images and use them to fly an autonomous drone. You do not need any other sensors other than a camera itself. So clearly with these applications, the scope of deep learning, especially for high bandwidth computations, has been evolving over the past 100 years. As these applications evolve, we are moving towards more smaller, faster and riskier applications. So as the applications of deep learning have been evolving in these areas, there is a very important question that we should be concerned about. Given that these models are highly they are not really a convex model, they are significantly non-convex. We can still use traditional convex algorithms, convex optimization algorithms like SUD to optimize them. So this is an important question because without having these models which can work with very simple optimization functions, we would not have, it wouldn't be possible to train these models on larger data sets or many more number of parameters. So recently a study analyzed how we can actually still optimize these models which are significantly non-convex using a very simple optimization methods. And the reason behind that is that these models are highly over-parameterized. They use millions to billions of parameters. So because of that, there is, if you see the manifold of these parameters, you will always have some optimal parameters somewhere in the proximity. So even if you start from any starting point, you will converge to the optimal point very easily. So that really helps to address the challenge related to training, given that you can use very simple methods and you can train these very complex models on a huge number of training points. However, whatever you solve in the training side now actually haunts you in the inference side. Because these models have a significantly more number of parameters. When you compute with them, it consumes a significant amount of data traffic from memories to processor, and that becomes the key bottleneck. Right? So now, given that these models have a lot of parameters and the bandwidth from memory to processor is the main bottleneck, it also requires to rethink the hardware, the architectures, computing elements, circuits, transistors for these methods. Right? So this brings me to the first point that I will take in this talk, is that what can we do, how we can rethink these architectures to significantly enhance the energy efficiency of computing, of deep learning. Right? So on that front, multiple techniques have been evolving in the past couple of years. One of the techniques actually uses distributed memory systems, a spatial digital architecture as shown here. By making use of memories more judiciously, you can minimize the data traffic. The second approach that has been taken by different groups is to bring computations closer to memory, to do a lot more near memory computations to avoid this data traffic. Even better than that, you could actually use your memories and do all the computations there as well. We think of memories. Here you are not reading the parameters out of the memory. Parameters are stored in the memory, but you are directly reading the output of a much larger function than the storage value itself. And this approach has shown orders of magnitude more improvement compared to any other schemes here. Even though there are a lot of advantages in computed memory, it comes with its own set of challenges. One of the challenges is that computations here are analog in nature, so you need to embed these memories with a lot of ADCs and DACs. Recent techniques had to involve one DAC for every bit line, so you can imagine a huge overhead because of that. Often in these cases, you are doing computations over bit lines which are very capacitive, so that also consumes a lot of energy. Because of these analog computations, you are also susceptible to process variability, and these cells also become more area expensive because they need to integrate both functionality, storage, as well as computations. And often, that has been a very key limitation of computed memory is that these methods have only worked for low precision computations very well, but for many complex deep learning tasks, you need to compute with high precision models and high precision computations. We can solve a lot of these problems by reconfiguring our data flow. So for example, in many of these methods, when we apply an input, we are directly applying an analog input to memories, right? So that requires embedding a lot of DACs, as we saw in the previous slide, at every column. That we could avoid it if we can actually do all the computations completely digitally. So we can project the bit plane-wise digital planes on the memory, and we can do these computations, right? This would be a very naive way, and the reason why it is not done is that because it would really require a lot of cycles to do those computations. If you are computing for an 8-bit processing, it would require 64 cycles, so that will completely overwhelm the efficiency of these methods. To solve these challenges, there is a lot of work going on in designing better circuits, better DACs, better memory systems. But in our group, we have taken a different view to solve this problem. Instead of just focusing on circuits, we have been thinking how we can actually change the mathematics of deep learning models itself so that we can make them better fit for a computer memory system. So can we redesign the deep learning maths itself rather than just focusing only on circuits for these computations? And what we found is that indeed it is possible to do so. So typically for any deep learning computations, a scalar product is the one, which is basically computing the vector product of input and output. Here, we took a different operator to multiply, to operate inputs and weights together. So here in this equation, what we are doing is that we are multiplying the sign value of weights and multiplying that with the absolute value of input, and then adding that to the sign of input with the absolute value of input. Right? Because sign is just +1 or -1, it is essentially multiplication free. Right? So this basically solves this problem that the typical computed memory faces right at the root itself by adapting the math itself. Because here we can decouple the operations between multiple precision inputs and outputs, inputs and weights, and that simplifies the implementation of computed memory in these cases. Okay, and we found some more advantages of this operator, that this operator is non-linear by itself, so you don't need an additional value or need any other layer after this. So that also reduces the number of steps that you need for this design. And this operator works very well. We have tested it on different data sets, compared it against other low precision cases, and it can track the accuracy of a typical operator very well. As you can see the results on MNIST and increasingly more complex sets like CFAR 10 and CFAR 100, there it can actually match the accuracy of typical operator very well. Right? So we can, by co-designing the mathematics of deep learning with computed memory hardware, we can solve a lot of problems without making our hardware necessarily more complex in these cases. So this is a very simple implementation that we performed for this operator. This SRAM is a typical 8-transistor SRAM cell, and you can apply the inputs. Along the bit lines, and you can do the computations row by row, and you can accumulate the output by summing all the bit lines together. Another interesting feature that we showed is that you can use memories not only for storage and computations, but you can also exploit the same bit lines for digitization also. So we showed this style of doing data conversion, which we call as the SRAM immersed data conversion, where the same memory array can be used also for digitization, right? So what that basically achieves is that you do not need to spend any more physical resources for building an ADC, because you can use the same memory array. That means you can pack a lot more compute power within a limited footprint to do all these operations a lot more efficiently by exploiting memories also for digitization. So So we have shown some of these designs by tape-outs. In this design, we showed that not only you can do a simple digitization steps like SAR ADC, but you can also hybridize them, and you can couple different memories arrays and come up with a very interesting architecture where memory arrays are doing all the computations for your design. A very key metric that everybody tracks for these designs is TOPS per watt. That means how many tera operations per second per watt you can do. And we have been able to get very good numbers. So here, the number that we got was 1 of 5. But you should also consider the technology node and the weight bits. So many of the other competitive techniques, they were operating at low bit precision, so they are only good for simple tasks. But for more complex tasks, they lose accuracy. So now, given that we can use computed memory, we can significantly enhance their efficiency to do very complex computations. But even that is not going to be enough for many of these application cases, right? Despite having the best deep learning models, our autonomous vehicles are still susceptible for failure. They can still crash. The best apps from Google still make an error, and sometimes these errors could be very serious. The basic reason why deep learning models cannot be guaranteed to be entirely accurate is that because the training set and the testing set could be significantly different, right? So for example, if I'm building a model today, and if the application domain can change over the past couple of years, that my model is not going to maintain its accuracy on those cases, right? In many applications, it's very hard to see how the application domain will evolve over the next couple of years, and we cannot prepare a training set that can capture those characteristics in advance. So this becomes a very important, very practical concern for many cases where the application domains could be very highly uncertain, and it can evolve, it can change, and your training set may not be applicable for those domains in the future, right? So here I'll just take a step back and I'll just think a little bit about how as a human we deal with uncertainty in the world around us, right? So let's take a set of banana images. We trained a deep learning model on that. If I ask a typical deep learning model by showing this image, what this image is, the model will say it's a banana, which is a correct answer here. Next time, if I show it something that looks like a banana in this case, which is actually a banana slug, but if I ask my model what this image is, the model will incorrectly say that it's a banana. But if I ask you the same question, that what is the image over here, you would say that it looks like a banana, but you are not sure. So by expressing the uncertainty when you are making a prediction and by not being definitive about it, it's a very important feature that we have that allows us to operate reliably in this highly uncertain world, right? Currently, many of these deep learning models, they lack this capacity where they cannot express their uncertainty when making a prediction. And that becomes the main reason why we cannot use them, we cannot not apply them in highly unreliable and uncertain world around us. So how we can bring this self-awareness where the models are aware when they might be wrong is a very important feature that we should also be looking after when we are building these hardware for us. Right? So what we have been also looking into to extend the computed memory for more probabilistic predictions where the prediction will not only be energy efficient and scalable, but they will also be self-aware when the inputs are highly different compared to the way the model was trained on. There is a field of deep learning inference which is called the Bayesian deep learning that has focused on it for a while. So here we take a Bayesian view of making a prediction instead of just doing scalar products for inputs and vectors. We do integrals. We just assume our weights are all distributions, and we perform all the operations by applying the Bayes law. So this works very well theoretically, but in practice it's extremely computationally expensive, right? So forget about doing these operations for more complex tasks. Even for some very simple models, it would take you days to make that prediction using the Bayesian deep learning model. There are ways to approximate it. For example, you could do Markov chain Monte Carlo approximation that can reduce this complexity, but it is going to be orders of magnitude more compared to a typical deep learning computation system. Right? Because in the last last line, you can see that these steps will involve sampling from a very complex density function to create multiple scenarios of how the world might look like to a model, and then computing output on each one of them, and then accumulating everything to make the net prediction. That will involve multiple cycles of making these samplings and inference and accumulating the outputs to make the prediction. Right? Fortunately, we have shown that even computed memory methods are very good for these sampling steps, which can reduce the necessary cost for these steps, and could be a very good fit for that. Okay. So that brings me to the last question that I'll talk about in the next couple of slides, is that how, in addition for energy efficiency, how we can also bring self-awareness in our computations and exploit computing memory as a paradigm to do those computations for deep learning. So there has been a lot of work to simplify the Bayesian inference model. One of the leading approach is variational inference. Even in variational inference, multiple methods have emerged. A very simple method was shown a couple of years back. It's called the Monte Carlo dropout method. The idea is pretty simple. When you are training a deep learning model, you use dropout layers at every output, right? During inference, we shut down these dropout layers. In this method, we keep them active, right? So we keep them active, and we make multiple passes of the input from the network to accumulate all the predictions to capture the uncertainty of the predictions from there. Okay, so this may look like this, that you have an input and you are randomly dropping neurons as you are making a prediction. So red ones are dropped, and when the inputs are changing paths, they are naturally capturing the uncertainty of the predictions in this case. So I'll discuss the three key opportunities that we explored for doing these kind of probabilistic computations using computed memory in the next couple of slides. I'll show that how we can use memories for sampling also, how we can actually do these probabilistic sampling in the memory itself. The second thing, I'll show that how we can redesign the compute flow so that we can share a lot of computations and we can avoid doing things multiple times and save resources while doing that. And the last thing, I'll show that given that we have to do these number of sampling and evaluation operations, is there a specific order by which, if I can execute them, can I minimize the necessary workload in those cases? So we showed in one of the designs that indeed it is possible to do very efficient sampling in the memory. You can harvest short noise from different bit lines, and you can build very reliable, very efficient sampler in the memory itself to do these probabilistic computations within the memory itself. We also showed that you can redesign the computations by making this very simple observation, is that as you are dropping and activating some new neurons in every cycle of dropout, there are some computations which are shared. If you are cognizant of that, then you can redesign the workflow so that you can avoid doing those overlapping computations in the next cycle and make your designs more efficient. The last thing that we showed is that if we can redesign these computations in an order by invoking different optimization approaches, then we can further make it more efficient to do these computations in memory. Right? So the idea here was that, let's say if I have to do all these computations which are shown as circles over here, we are searching for a specific path to do those computations, which will minimize the necessary workload, where these edges are showing you the workload from one sample to another sample, and by optimizing the order in which these computations are happening, you can make them, you can significantly minimize the cost of these computations. Right? So this example will further clarify what it basically achieves. So let's say if I take MNIST, I have trained my model on the regular images. Next time when I'm testing it, instead of passing the typical images, I'm passing a character tree which is slightly rotated from its initial position, right? So the network was not trained on image sequence from 2 to 12, which are kind of rotated from the original location, but it was only trained on the very first image over here. If you pass these kind of inputs to a classical network, it will be forced to predict one of the letters from 0 to 9 for these images. But what we hope to achieve is that when you pass these kind of inputs which are different from what the network was trained on, it should be able to express its uncertainty in those predictions. So in this case, let's see the output that we get from the network on these images. So as long as the images are very similar to the training set, you have a very confident prediction where output class for 3 is 1. But as you rotate these images, then you have a prediction in every iteration, which is all over the place, that shows that the network is not really sensible in those cases. Another example is shown here is that where we are tracking a drone's position. So the black line is the ground truth, and these dotted predictions are the ones which are coming out of the network because it's making a probabilistic prediction for those cases. And in this case, if we see the prediction post error, the prediction error versus the uncertainty of the prediction, we see a very good correlation. So this is a very interesting feature because even given that we cannot guarantee that a deep network is always going to be accurate, as long as it can indicate that these are the cases where I am going to be inaccurate, will be highly useful for cases where we want to make a more risk-aware prediction. Right? So that brings me to the conclusion of this talk. So I've shown that in addition to energy efficiency, there are more merits that we should be looking after for deep learning. Being robust and being aware of the uncertainty of the application domain is one of them. I've shown that computing memory could be a very good pathway for these computations where you can achieve energy efficiency as well as you can get these robust probabilistic predictions from the network. But the key to achieve these features is going to be co-design. We significantly co-design the model, we co-design the variational inference processes to keep the circuits as simple as possible by adapting the mathematics of these computations to do these computations in very limited resources and limited power to achieve this efficiency. Okay. So thank you so much, and if you have any questions, I'll be happy to discuss that. So we are doing the fixed point, fixed chain computations 8-bit, but it can be reconfigured to 6-bit or 4-bit.
I mean, this weight is stationary data flow or some other?
It is going to be weight stationary, right? Because you are doing the computed memory, so it's better to keep the weights fixed in the memories itself.
And so how to handle the partial sums? Because in weight stationary approach, lot of partial sum is weight.
Right.
So how you can handle in your architecture?
Right. So I think the partial sums will still require using an analog to digital converter. So you do computations at every bit line, and then you merge them all together to exploit Kirchhoff's law to avoid any error over there. And the output is produced like as a voltage that can be digitized to compute the net output of the design. But for the digitization part, as I mentioned, that you can still use the memories itself, and you do not need a dedicated ADC to do those computations to minimize the overall resources for the computations.
And what is the weight mapping approach? You are showing row-wise or column-wise?
So weight for a vector are actually arranged row-wise, right? So you apply the entire vector of inputs along the column, and likewise weights for every channel are also managed are stored along the row-wise.
That was, yeah. What was the neural network model that was used?
Right. So for CFA10, I believe that we were using. I
standard transistor pixel.
Yeah.
You have connected two internal nodes to the pre-charge, but it is a transistor inverted back-to-back connection, right? Then how it will be stored always be one.
So I think the design that I'm using is an 80SRAM, right? So
one of the circuit. Yeah, this is
okay.
Here.
Yeah.
So the top of the circuit is 60, right?
So this is actually the design of sampler. So this is what it is doing is that each of these nodes, each of these ports which are connected to the right word line, they are going to be off. So they will produce a short noise. This short noise is being harvested along the column. And because of that, we are using this typical random number generator, which is a bistable circuit, which is pre-charged, and then when you force it to settle down to 0 or 1, based on the noise, it will arrange itself to 0, 1, or 1, 0. Right? So this is not for computations; it's basically for sampling. Right? As I mentioned that we are doing uncertainty-aware computations that requires probabilistic steps. So those steps can also be implemented within memories by harvesting the short noise and doing these computations in the memory. Yes.
Okay, so our next speaker is Mr. Saurabh Goyal. Saurabh Goyal has received his BE degree from Delhi Technical University, Delhi. He is currently working in analog design team at NXT Bangalore. He holds 10 US patents and 1 defensive publication. He has worked on power management, USB-5, high-performance oscillator, temperature sensor, over-voltage protection circuits, sigma delta ADC and gigahertz multiplexer units. Please welcome Mr. Saurabh.
Hello everyone. So today I will be presenting a paper on design challenges and techniques for 5 nanometer FinFET CMOS analog mixed signal circuits. So directly going over the paper. So there are a lot of benefits of CMOS scaling for digital circuits like low area, better speed and less power. But for analog mixed signal circuits there are a lot of challenges. So first one is that the threshold voltage of the FinFET is not scaling as the supply voltage is scaling down. And as L gate is going down, we have 6 nanometer in this technology, so more leakage is coming from the transistor, and the layout rules are becoming more and more stricter, and mostly of them are density related. So this paper addresses common AMS circuit issues. So the first one will be the leakage in the dummy transistors. The second is interconnect parasitics, and the third one is gate-induced drain leakage. So going over the brief introduction on the continuous active area in 5 nanometer technology for better density and better performance. So if we see the image on the left corner, in higher node technologies we have a active gate which I have shown in the red, and then we add dummy devices which are gray, but they don't have a shared active area. But now to have a better density in lower technology nodes, we have a continuous active area style where we share the active area with the dummy gates also. So if you see the green, which is the active area, it's continuous with the active gate as well as the dummy gates. So the benefits of continuous active area is basically we have a less mobility variation and better matching. So if we see the image on the right hand side, so if we don't have dummy devices, so the bottom inverted U, we see we have a mobility variation in the shorter area, because if we will have a stress from the outside, the mobility will vary. But if we add a lot of dummy devices across the active gates, so that time the dummy device build a stress plateau, and they will take the stress from the outside, and your mobility for the active devices will remain same. But if we add the dummy devices, we will have more leakage to the dummy devices, as well as it will add more area as well. So the first one is leakage in dummy transistors. So I will go through the problem first. Okay, so if we see the image in the bottom, so we have a dummy device which is gray MD, and we have 2 NMOS transistors M1 and M2, which are the active transistors. The dummy transistor gate is connected to a VSS, and now if they are sharing the same active area which is green, and if signal 1 and signal 2 are at the different potential, so the leakage current can flow from the M1 to M2 transistor. And the right one we have is when we have the dummy transistors at the end. At that time, all the terminals of the dummy gates are connected to ground. So the leakage current can flow from signal 1 to the ground, and then signal 2 to the ground. So the solution for this can be if we add more number of dummy devices and float their intermediate nodes. So basically, if we have, instead of having a 1 MD transistor, if we have a transistor from MD1 till MDN, and basically effectively increasing the L gate of the dummy transistor so that the leakage between the signal 1 and signal 2 is less. Similarly, if we have dummy transistors at the end, we can float their source and drain nodes and effectively increase the L gate in that case also. Okay, so this is one of the example of the registered DAC ladder. This is the DAC we have used in a free running oscillator. And this reference voltage generator consumes 2 microampere of the current. And if we see switches in the red highlighted area are the fine transistors. And this is a 7-bit decoder, so basically we have 128 transistors and each fine resolution is of 1 millivolt. So basically a small leakage through these transistors in the dummy devices can disturb the VRF accuracy. And if we see the simulation number at 125C fast corner, we see that the leakage, if we don't do anything, then the leakage will be 280 nanoampere at this corner, and which will disrupt the frequency VRF by almost 13 millivolt. And similarly, we insert the dummy devices to increase the L gate. The leakage has been reduced to 57 nanoampere, and the VRF remains same at 540.3 millivolt. So the next topic is interconnect parasitics. So if you see the image on the left, so basically if we are scaling down the technology like from 16 to 7 and then 7 to 5, the parasitic resistance is basically increasing by 3x. And the cap is also increasing because of the coupling of the cap to the contacts of the transistor. And this is basically, increasing the lot of iterations between the pre-layout and the post-layout simulation. So if this is a basic 5-stage ring oscillator to show these results. And if we can see that in the pre-layout simulation, the frequency was 7.13 gigahertz. But as we post-layout that block, and we can see that the frequency has dropped from 7.13 gigahertz to 5.85 gigahertz. So we have done basically a few modifications to achieve that frequency back to 7 gigahertz. We have used the continuous active area layout style, which has reduced the length of oxide definition effect, which I have already discussed. Instead of using 8-track metal zero routing over the MOS gates, we have used 3-track metal zero. So if we see the image on the left corner, so from 8-track, the frequency was 5.71 gigahertz, and it has increased to 6.37 gigahertz, which is kind of 10% improvement in the frequency. It has basically reduced the cap and helped in achieving this frequency. We have used wider M0 to reduce the parasitic resistance, and the CGS reduced by minimizing the overhang of diffusion contacts beyond the active area. So we have reduced the contacts as well. And instead of using the conventional floor planning of the ring oscillator like 15243 horizontally, we have changed the floor plan also to the vertical, which have reduced the interstage routes between the stages and helped in achieving more frequency. We have used a wider metal layer to reduce the parasitic resistance. Okay, so after doing all those several layout iterations, we can see that the frequency which has been dropped to 5.85 gigahertz has been brought back to 7.01 gigahertz. And the V-ring means the CCO supply, which was increased to 0.804 volt, has been remained same at 0.809 volt by getting the same frequency of 7.01 gigahertz. So we have not violated the reliability limit of the transistors that we have used in the ring oscillator. Now the third topic is gate-induced drain leakage. So gate-induced drain leakage basically is caused by the high potential from drain to gate when your gate is at the lower potential and your drain is at the higher potential. This basically happens due to band-to-band tunneling in the gate-drain overlap region, because your gate is at the lower potential and if your drain is at the high side, so the minority carriers below the gate can transfer from the gate region to the substrate region, and that leakage can flow. And it increases exponentially as our VDG will increase, so there will be a cutoff where it will increase exponentially. And it's directly proportional to the gate drain overlap area, so if you have more gate drain overlap area, then this leakage will be higher. So as shown in the left image, so we can see that the red one is the Gödel current for the NMOS and the blue one is for the PMOS. So above 1.2 volt in 5 nanometer, the leakage current is increasing exponentially, and similarly for the PMOS below 0.4 volt, the leakage is been increasing. And this current is very critical for the performance of many mixed signal blocks like SAR ADC, because there we are sampling the signal, and if this contributes to the leakage, then we basically distorting the signal itself. So one of the technique that we have mentioned over here is, let's suppose we have a sampling switch M1 over here, and if we somehow can sense the drain voltage of this transistor, and if we see that the drain voltage is greater than the girdle threshold, we can raise the gate voltage by 300 and 400 millivolt to reduce the basically VDG of this transistor to below the girdle threshold. And if we see that the leakage reduction with the proposed solution, so blue one is with the above mentioned technique. So the leakage means the current has become almost zero if we use this technique, because we have reduced the girdle threshold. Below the girdle threshold, the leakage is almost zero. So we have basically brought back the VDG below the threshold value. So this is the conclusion slide. So we have addressed few challenges in the 5 nanometer technology. So leakage currents in dummy transistors, interconnect parasitics and gate-induced drain leakage. And these explained techniques are effective in order to meet the required design performance. So in lower technology, we have to put the dummy devices. It's mandatory for the performance as well as the density. We have to put, and those should be in the continuous active area. But the thing is, those dummy devices, source drain and gate should be connected to VSS for NMOS and to the supply for the PMOS. So they will have the leakage for the short. Means dummy devices are there for the short. But we have floated their intermediary nodes, like source and drain we have floated. So basically, if we added, let's suppose 10 devices, so before that the length was 6 nanometer, let's suppose, and your drain is connected to the ground. So you have the leakage that is going to the ground. But now you have 10 devices, basically means we have 60 nanometer of the length. So basically, if we increase the length, then the leakage will automatically get reduced. So that in that way we have reduced the leakages in that.
So I'm talking about the challenges. See, LVS is one of the challenges, and
yeah, LVS and DRC passed.
And the second thing is, when you have the floating node, because the interconnecting dummy devices, they will have the floating nodes, right? So we we run checkers, dynamic checkers on the circuit, whether if there is some problem in the connection or some problem in the design. So that will start, that will start failing, because there are a lot of high Z nodes in the design, and the report will be flooded with those high Z nodes. So that is, again, one of the challenges that probably, then it takes more time to the analog verification engineer, I would say.
Right, but actually means meeting the design performance is the first thing than doing all those checks. So we have targeted the design performance than those things.
You had M0 before in the design and made it wider to reduce the gap, or it's that M0 is introduced in certain passes, like only in dummy devices you had M0 and you could reduce the gap from that. Basically, where is the M0 introduced, wider M0?
Okay, so you are talking about MD, right? This MD. So see, you understand about this continuous active area, right? For dummy devices, we should have this continuous active area in the lower technology. So the gray one is a dummy device. So and the green one is the active area. So we have dummy device in the active area also. So this MD device is already there. Means this dummy has to be there, otherwise you cannot have a continuous active area layout style. So now if you have only single dummy device to maintain this technology rules, you will have a leakage that will be flowing from signal 1 to signal 2. So we cannot touch the active gates because those are our design transistors. We can only change the dummy devices. So basically we have increased the number of dummy devices because those are not part of our design. So we have increased the dummy devices and effectively increased their L gate to reduce the leakage between the two active signals.
No, I'm talking about the M0 method, wider M0 method.
Okay, ring oscillator you are saying.
Yes.
Okay, so what is the question?
Where did you introduce this M0? You mentioned you used a wider M0, right?
Right.
Yeah. So where did this wider M0 get introduced so that you could reduce the leakage? Because there could
It's not for the leakage, it's for the parasitic resistance.
Yeah.
It's
for the coupling capacitance or something, right?
No, if you use the wider M0, that time you are lowering the parasitic resistance, right? It means wider metal zero. This is not transistor, this is wider metal zero.
My question is, M0 was there before and you made it wider, or you introduced a wider M0?
No, we have introduced the wider M0.
Okay, thank you.
First of all, related to the leakage reduction, when you are introducing so many dummy devices, are you able to meet your area specifications? I mean, area is not of concern in your IP things. Is that the case?
Yeah, because we are in the lower technology, right? So the area is not a big problem if we add one dummy devices versus 10 dummy devices.
So it is only for selected blocks where area is not critical. It cannot be widely used in a full core, let's say, for all the different...
Yeah, no, basically wherever we need a leakage reduction, we can easily use this technique, I think. Means because we don't need, and everywhere we don't need this leakage reduction, right? So at few of the key blocks we will be needing these techniques, there we can introduce this thing. So area will not be a problem in that.
My second question is related to the, I think the reduction which you observed in the ring oscillator. You are adopting a technique to say that from 7.1 gigahertz the reduction of 5.85. My point is that when you improve that, this is a very, let's say, it's not a representative number because it is only one process power. If I validate a, let's say, oscillator over PBT, anyway there is a wide variation, right? So what is the actual relevance of just reducing from 7.13 to 5.85, which you want to compensate? Because if I do a PBT over 7.13, there will be a variation. If I do a PBT over 5.85, it will be a higher variation because the process of the capacitance resistance will be changing.
Right.
You have some studies to benchmark that effectively if you keep the same frequency, the variation itself is still controlled, or you are losing everything in terms of variation?
Okay. So basically this is at the typical corner, and if we have the frequency that is going down from 7 gigahertz to 5.85 gigahertz at the typical corner itself, that itself is a problem for us because we cannot tolerate that. So to achieve the frequency back at the typical corner itself, we have done all those modifications that I have discussed. Now the next question is about the PVT that you are saying. So in the PVT variation, I can understand that it can be higher or lower in the pre-layout and the post-layout, but our main target was to get the frequency back first at the typical corner itself, and then we have tackled across PVT for pre-layout as well as the post-layout simulation.
You are getting a benefit even at the post-layout?
Yes, we are getting. Yeah, because the parasitic resistance is also increasing in the post-layout simulation.
Is it RC network simulation?
Yeah, it's a RC network simulation.
Okay. And in the GIDL slide, right?
Yeah.
So what kind of MOSFET was what was the limit of the voltages?
For your single threshold?
Not threshold. Overstress limit of the device. Like what kind?
This is 1.5 volt transistor, and the overstress is 1.65 volts.
And the dummy device, what you mentioned, right? Basically, I have worked in 7 nanometers. So 7 nanometers is a port, right, which we have to put. So is the same kind of you saying, or is this a separate dummy device in 5 nanometer?
Port.
I mean, so at the end of the active, right? There is a dummy poly. So is it? But that we can avoid if we overlap the, let's say, with NMOS and PMOS stack, right? Overlap the source of the drain of the PMOS with the drain of the NMOS. We overlap that we can get rid of.
No, it's different. We have to put these dummy devices because, as I've shown in the first slide, right? So basically, they create a stress plateau also. If you don't add the dummy devices over here in 5 nanometer, so your mobility will vary a lot for the NMOS and the PMOS.
There is a design rule that after certain micrometer, we have to put a dummy device.
Yes, like the example I've shown for the resistance ladder where I have 128 fine trims, which is So it's a rule that you have to put a 5 micrometer dummy devices across those transistors.
That dummy devices are put in schematic also for my channel?
It's not necessary that we have to put in the schematic, but we have to put in the layout.
So even if the continuous active also, you have to put in dummy poly in between.
That's right.
Okay, thank you. Sorry to interrupt.
Volunteer over there who's going to raise, after 13 minutes, he's going to raise his hand just to warn that we have to wrap it up. We are running actually 15 minutes late this session, so we have to make up for the time. Thank you for the cooperation, and we'll entertain only 2 questions for every speaker from now on, just to make sure we finish in time.
Thank you. So, next speaker is Mr. Mohammad Saqib Ansari. He received a BTech degree from Mahatma Jyotirao Phule University, Bareilly, India in 2020. And yes, he is currently working with Mahindra & Mahindra Limited in the automotive division as a research and development engineering. Mahindra Research Value Channel. His research interests include soft errors in digital circuit and embedded systems. Please welcome Mr. Saqib Ansari.
Thank you for introducing me. Very good afternoon to all present here. So today my paper I will discuss about design of radiation hardened 12T SRAM with enhanced reliability and read or write latency for space applications. So coming to the today's agenda, so first I will talk about overview, then next I will go to the problem statement, then scope, then proposed solution, what we have proposed, then methodology, what we have used, then results, what we obtained, and then conclusion, and then referrals, which paper we have selected for referrals, and then at last we will be having a question and answer session. So coming to the overview of the presentation, like work what we have done. So as we all know that circuit continuous downscaling of the integrated feature size, the reliability has come to bottom line. So I'll just try to tell Moore's law, as we all know that in every 18 months of time period, we are implementing double number of transistors over or a particular area. So with that, what is happening? This memory cell or any kind of circuit is getting small. Size is decreasing. So because of that, what is happening? The capacitance of the particular node where the data is stored is lowering. Means the charge which is required to store the data is small. So if any kind of noise is entering to that node, so what it is doing, it is just changing the data. So that is what we will see in the next slide. So if the noise is happening at a particular memory cell, so that is called as single event offset. The same noise is occurring at the combination logic circuit, so that is called as single event transient. So in the left side, we can see this is basically a combination logic circuit. So if any noise is happening at the D flip-flop, so what it will do, it will create single event transient. So that noise is basically coming from the outer space, that is basically a cosmic rays or alpha particle. So these cosmic ray and alpha particle, what they will do, they will be having high energy. With the help of high energy, they will just flip the data or value what is stored at that particular node. If we talk about 60 SRAM cell, here you can see we have 2 nodes where the data is getting stored. First is Q and another one is QB. So in this we have word line WL and bit line and bit line bars are there. So for writing any data in the circuit, we need to turn on the word line, and with the help of bit line and bit line bar, we can able to write the data in the circuit. So suppose we are writing 0 in this circuit, so according to that, Q will be 0 and QB will be 1. Both we have 2 inverters back to back, so it's a positive strong feedback system. So if we can assume that any particle strike at node Q is happening, So if it is having that much of energy, it can just flip the data, or it can provide that much amount of voltage. So the data what is stored in the node Q will be flipped from 0 to 1. Similarly, it is having positive feedback system. So because of that, the data what is stored at node QB will be changed. So what will happen now? Whatever we have stored the data as 0, it has become 1. So this is the main problem which comes when any cosmic rays or alpha particle will happen. This is not a permanent problem. This can be resolved. There won't be any kind of hardware or loss. We can say that if we are restarting our system or we are just rebooting our system, we can fix this. But there are some applications where we cannot change these things, that are like the space missions and military application as well as in avionics systems. So many places we are using SRAMs and all, like we talk about space applications, banking transactions, automotive railway systems, as well as ADAS system. Now, if we talk about automotive, so in few coming generations, we are going to use advanced driving assistance system. With that, what will be happening? We won't be driving the cars, so cars will be following. Cars will be automatically driven by the ADAS system. So these are the previously designed few SRAM cells. On the basis of that, I have just proposed a new SRAM cell. So on the left side, we can see this is a Quattro 10T SRAM cell. On the right side, this is a new Quattro 10T SRAM cell. So what we will do in this, we have seen in 60 SRAM cell, we have stored 0 at Q and 1 at QB. So same thing we'll do, we'll just make 2 other nodes with the help of transistor, and we'll just save the data at another node and when this particle strike will happen, so we'll just give the feedback again. This particle strike will be for short duration of time, so we'll just give feedback to it will automatically revert back to its original state. So on the right side we can see this is the proposed design. So it looks similar to new Quattro 20. I have introduced 2 more transistors, an M7 and an M8 as an access transistors. Already we have an M5 and M6 as an access transistor for enhancing the read-write latency and for increasing the critical charge at particular nodes. I have introduced 2 of these transistors. So first I'll discuss this architecture of SRAM memory cell. So as we can see in the architecture of SRAM memory cell, we have pre-charge circuit that is used for pre-charging the bit line and bit line bar. And this SRAM cell will be any kind of SRAM cell, 60 or whether it is 10T or 20. On the left side we have row decoders, that is for selecting the word lines. On the bottom side we can see column decoders. So column decoder is basically used for detecting the bit line and bit line bar data. And write driver is used for writing the data in the memory cell. Sense amplifier is used for basically sensing the data from that memory cell. So we have focused on static noise margin as well as critical charge. So this shows old static noise margin, read static noise margin, and write static noise margin. If we talk about the circuit which is capable of software, that is Quattro, new Quattro and proposed 12T. So our circuit is achieving old static noise margin, it is near about same. But if we talk about read static noise margin, we are improving the read static noise margin by adding the 2 transistors. And if we talk about write static noise margin, so we are achieving a good result in by adding the 2 transistors. Okay, so if we talk about Monte Carlo simulations, so we have done Monte Carlo simulations for writing and reading the data. So 2000 Monte Carlo simulations we have done. So in that we achieved there is no change of data while doing the Monte Carlo simulation. The circuit is working properly. In the middle we can see this is critical charge comparison. So for our proposed radiation ardent 12T cell, we are achieving better critical charge in comparison with the Q220 and U220 SRAM cell. The last one we have just shown, if we are injecting any particle strike at any node, so the circuit is able to return back to its original state. First figure shows about the comparison of hold static noise margin, read and write static noise margin, only write hold. If we talk about the read delay, mu basically denotes the standard deviation and sigma, mu denotes the mean and sigma denotes the standard deviation. So if we talk about read delay, so we are achieving lesser read delay and the standard deviation is also less. Standard deviation means the deviation of the values which we are getting after doing 2000 multiple simulations is less. Similarly, if we can see for write delay, we are achieving less write delay for our proposed 20. And if we talk about critical charge, what we have calculated after 2000 Monte Carlo simulations, so in that we are achieving better critical charge. Basically, if we want to tell about what is critical charge, this basically minimum charge required to flip the data at a particular node. So this is a tabular representation of the values. So in this we can focus on leakage as well as area. So first I will come to area. So 60 SRAM, we are having a lesser area. And if we talk about new quadrant proposed 12T, we are having equal area. So we have just maintained the symmetricity as we can see in the layout. And if we talk about the leakage, so we have increased 2 more number of transistors. So because of that, we are getting more, little more leakage power. So these are the references from where I have just, okay, so coming to the conclusion, so we have designed a VLSI SRAM cell that is based on the new Quattro with new Quattro 20 with enhanced read and write delays as well as with improved noise margin. And if we talk about single event upset, so the circuit is immune to software. So our simulation shows that the standard deviation achieved for the read and write delay is minimal when compared to Quattro 20 and new Quattro 20. So the proposed cell has strong write static noise margin as well as shorter read and write access time. So in comparison to new Quattro 20, the proposed design consumes nearly the same area. So the proposed cell can be used for aerospace applications.
Can you please radiation hardened cell?
Yes.
What is, how does it compare with the 12 transistor dice?
With other 12 transistor we didn't do now. We have just done with the NQ20 that we are in line to do that.
And this work is at which technology node?
This is at UMC 65 nano.
The next paper is authored by Sweta A, Abhishek Upadhyay and Bhupendra Singh Reniwal. But Mr. Shakib Ansari will be presenting the paper on behalf of the authors. And in case if you have any doubts or queries or questions related to this work, you can directly contact him offline and he can note down the questions and it will be communicated to the authors.
So this work is done by Sweta, as already told by sir. So this is based on a design and analysis of multi-bit multiply and accumulate, that is MAC unit, analog in memory computing approach. So coming to the today's agenda, first I'll talk about overview, then problem statement, then coming to the scope, then proposed solution, methodology, what they have used, then coming to the results and then conclusion, then at last, if you have any question or answer, you can just contact me. Yeah, coming to the overview, so as we all know, one Newman architecture on the right side is mentioned will be having memory and logic. So one Newman architecture came to bottleneck as it is energy hungry, having energy hungry data transfer. It is having long memory access latency as well as it is having limited memory bandwidth. So the movement of data is taking more energy than what is required. So that's what we are moving to in memory computing. So in memory computing, what will happen? So that arithmetic logic unit as well as the memory will be doing simultaneously. That is parallel local data processing will be there, and it will be having short memory access latency, and it is programmable and will be having low cost. So this is dual mode computation memory simultaneously we can do as the storage as well as ALU. So coming to the problem statement. So the architecture is based on bit line discharging through the column of static SRAM arrays. So word line applied to the memory cell are taken as the operand, that is V in, and the other operand is the value which is held inside the memory, that is W. So the voltage is charged by the bit lines passed through the combinational circuit to obtain analog multiplication results. So DAC is basically used to embed the word line, and the ADC used to obtain digital result for further usage. And in combinational circuit, we can see we have used current mirror circuits. As we can see, this is the current mirror circuit having two transistors PM1 and PM2, and 60 SRAM cell, normal conventional 60 SRAM cell will be there for 256 by 256 arrays. On the left side, we can see the row decoder that is used for selecting the bit line, word line. And at input, we have connected 4-bit DAC, and output we are taking through the ADC that will give the dot product of the results inputs. So coming to the next scope, what's the scope? So application that handles large amount of data can be benefited from this technology, because this in-memory computing will be having very faster processing, so it will reduce the latency as well as the power consumed by the reducing that we need for input-output operations. So most of the applications like machine learning, artificial intelligence, and hyperdimensional computing need multiplication, so that multiplication will be done faster. The reason why they have chosen SRAM, because SRAM is very popular, it is cheap, and it is already used in various data processing hardwares. So this is the main, we can use that as main memory. So coming to the methodology, so in this bit line and bit line bar of each column of the memory array is discharged through the current mirror what we use. So the bit significance of individual bit of the result is exerted with the help of PMOS current mirror circuit, that is current mirror sizing we'll do, that is mentioned as I output upon I input, that is W2 by W2 upon L1 upon W1 upon L1. So in the figure you can see this array of 60 transistors, they have just written in a numerical expression like 2 cube W3 plus 2 square W2 and 2 power 1 W1, 2 power 0 W0. On the left side, P3 is the most significant bit, and P0 is the least significant bit, and for the ratio they have used is 8:4:1 for the approximation ratio of the current mirrors. So coming to the results again, so linearity plot for all the dot products for 4x4 multiplication is done. The output is shown on the right side of the slide. That is in between analog product acquired for 256 combinations of 4x4 multiplication plotted against expected dot product. So that is indicated by V out in the circuit. Observation what they have observed a certain level of non-linearity in this. So if we talk about the effect of V in on output, if they are varying W is basically the word line charge. So by keeping the word line voltage as constant value, the bit word is varied to obtain a plot against the analog output voltage, and linearity is obtained when the effect of VE is observed on varying the W. So if we talk about V in on output for Effect of W on output for varying the VIN. So by keeping the bit line as a constant value, the word line voltage is varied to obtain a plot against the analog output voltage, and the observation observed during this is they found non-linearity in that. If we talk about internal non-linearity, so basically it is deviation of actual product from the expected product. So on the x-axis we can see expected product, y-axis it is integral non-linearity. So for LSP they are achieving 0.3, positive 0.38. If we talk about delay, power delay product and power, so the comparison between IMAC, bitline shifting and the proposed work, one by one we'll see. So in IMAC circuit, what they are using is clock and synchronize. It is synchronized and dependent. So because of that, it is the delay is getting increased, and higher operational time and rise in the voltage for each accumulation leads to high average power consumption in IMAC. Best performance is observed at VDD equals to 1. So if we talk about bitline shifting, operands are cycled through a sequence which introduces a heavy delay element which is additive through each combination. So low power dissipation, then IMAC going to minimal discharge operation. So poor performance is obtained below 800 millivolt VDD. So if we talk about proposed work, so computations are achieved based on the sizing, hence no other factor acting towards delay. So timing window during which the output is achieved is less when compared to the other low power consumption circuit. So the best performance is observed at VDD equals to 1 volts. So this is basically comparative analysis of the design, the related work like bitline shifting and IMAC, and proposed. Proposed thing is just mentioned in the table. The technology node what they've used is 90 nanometer. So coming to the conclusion, so in-memory computing is the future. Challenges of this work can come from the compilations that rise in designing of the ADC to account the INL, the sense amplifier. So the paper discusses the design, schematization and analysis of an IMC architecture using the PMOS current circuits.
Mr. Rupesh. So Rupesh Damodar Kadao is 2022 postgraduate student from National Institute of Technology, Goa. He completed his masters in VLSI technology and currently working in Global Foundries Engineering Private Limited as an intern in analog design. Please welcome Mr. Rupesh.
Good afternoon to one and all. My name is Rupesh Damodar Kadao. On behalf of all the authors, I will be presenting a 2.5 GHz 1 KB SRAM with auxiliary circuit assisted sense in 65 nanometer CMOS process. I will be walking you through an introduction, especially 60 SRAM, then operation of the SRAMs, especially the sense amp, then the two variants of the SRAM, sense amplifier, the conventional use strong arm latch sense amplifier, then auxiliary circuit assisted sense amplifier. We have done a case study. We will also discuss it on a 1 KB SRAM. Then we will discuss the simulation results and the performance result with the state-of-art designs. Then a conclusion. So the SRAM found its application in many of the IoT devices nowadays. So one of its application will be in storing the data. So SRAM will have mostly 3 modes of operation: read mode, write mode and a hold mode. And the performance of the SRAM can severely cause the speed of operation, and designing of the peripherals included can have effect on the frequency of operation. So basically SRAM is back-to-back connected inverters with 2 access transistors showing the states stored in the bit cell with the address line and the data line. Address line for the word line on bit, data line on a bit line. The figure B shows the write operation of one of the logic level in a bit cell, and figure C shows the read operation when we are reading some of the state stored in a bit cell. We will be more focusing on the read side as we will be discussing the sense amplifier. Sense amplifier will be included in read mode. In an array of a memory, a column structure is shown in the figure A. During read operation, it has a pre-charge circuit as well, a bit cell. A figure shows just 2 bits for 2 addresses, WL when WL is 1 and WL is 0. And it has a sense amp which will fed the output logic level to the encoded logic, which will be again detected by the sense amp. The differential output mode from the bit line, the figure B shows the differential bit line pair mean value for the differential bit line pair voltages of the sense amplifier. So it has standard deviation of 0.86 millivolt and a mean value of 10.04 millivolt. So we need to design a sense amplifier such that this mean value get readable by the sense amplifier to get the correct output results. Figure shows the conventionally used sense amp. It has a sense amplifier enabled signal SAE. Depending on the signal, when we are assessing the sense amplifier, it can have a read failure if we assert a sense amplifier too early or the delta VVL, that is the differential bit line pair voltage, is low, then we can experience a read failure. Otherwise, when bit line difference is high enough so that the strong sense amp can detect it, we can get an output. This read failure condition can be conventionally addressed with this in-house developed sense amplifier. It has the same structure as the conventional one, with additional circuitry being used to just pump the signal output node to the VDD and the ground, depending on the charging rate and discharging rate of the respective ones. So when the SA is low, M1 and M2 are on, so FN node and FNP node will get charged. So MR1 and MR2 will be on and output will get charged discharged to ground. So this will be, the output will get resetted. So we can call it as reset mode. When SA is high, initially M1 and M2 will be off. So FN and FN2 will start to discharge depending on the input logic level we have applied over V in P and V in M. Those are the differential inputs from the sense amp. The current flowing through M3 and M4 will vary. If, let's say, M3, V in P is greater than V in M, the current flowing through it will be greater, so the discharge rate will be greater. So we have here a feedback circuit, which feedback circuit can prevent discharging if a sense amplifier can detect the signal within a given period of time. This feedback circuit can help it. So if FNP start discharging, MC2 will be, so since the current is very large, MC2 will turn on first and output VP will discharge first. Still, MC1 is on, so MC2 is on, so MC1 is also on, and both will discharge, but discharge rate will define the speed of operation. So one of the nodes will discharge first, respect to the other. With respect to the feedback circuit, the node will restrict it from further discharging, and if we consider a VNP is greater than VNAM, then the output we will rise to VDD, and output N will rise to ground, will pull down to ground. If it is getting detected within a given period of time, then the additional circuit will still be in sleep mode. But if output node is not getting pulled up or pulled down depending on node's voltage level, so the sense amplifier will activate the additional circuit in the sense amplifier will get activated, and it will help to pull down or pull up the additional current, additional nodes by pumping in the additional current in one side and pulling it down or sink it down on the other side. The same operation will happen if VNP is greater than VNAM, or the input voltage will get reversed. So here we can illustrate, this is the final structure, final implemented auxiliary assisted sense amplifier. Here we have done a case study over it. So for a 1 kb of SRAM, it includes a row address of column address of 5:32 mux. It has an array of 32 cross 32 bit cells. So in each column array, we can see a pre-charge circuit, a 32-bit SRAM, 32-bit cells, a sense amplifier, and write circuitry. Depending on the address line selected, on a PC signal, the respective bit cell will get selected, and the state level will get reflected on a bit line pairs. So that will be get sensed by the sense amplifier, and it will be the sense amplifier will sense the logic level in the stored bit cell. So simulation results on a 1 kb SRAM show at a frequency of 2.5 GHz. We have performed operation like writing 1, reading 1, writing 0, and reading 0 in the respective cycles. Here we are showing the process variation results doing Monte Carlo for 400 number of samples for the differential bitline pairs. The smaller the, ideally we want the curve as small as possible. The figure B shows the variation with the bitline voltages with respect to the yield. We can see the more than 80% of the yield can be found when differential bitline voltage at 8.5 millivolt, and figure C shows the difference between the timing delay, that is delay with conventional and auxiliary circuit. We can see the improvement of 22.3% improvement can be happen, so that the speed of operation will get improved. The performance result shows a delay of 178 picosecond and write delay of 126 picosecond. We have implemented in CMOS 65 nanometer technology with a supply voltage of 0.9 volt, having a frequency of 2.5 gigahertz, which consuming the power of 13.5 millivolt, including all the peripherals, and timing margin improvements are we have observed at 22.3%. We compare it with state-of-art results, and we can show here the results. Concluding, the case study has been performed on a auxiliary circuit assisted sense amplifier. N65 nanometer technology with a supply voltage of 0.9 volt, which observe a delay of 178 picosecond for read and 126 picosecond for write, and a frequency of operation of 2.5 gigahertz with an improvement of 22.3% time matching. These are some references used. You can see the auxiliary circuit is getting activated unless the science amplifier is not unable to detect the initially unable to detect the output. So the power penalty, without significant power penalty, we are getting the same results with the improved in frequency of operation, with the speed of operation.
Thank you.
Thank you.
Let us thank the speaker. Yeah. Thank you everyone. This concludes the session 5B. So I would like to thank the speakers, the volunteers, the audio, visual, technical people, and the audience here for the smooth functioning of the session. Thank you everyone.
I'd like to thank the session chairs, Professor Abhishek and Professor Bidu. We will consider them with the momentum.
This is the session and last part of the conference, 36 VLSI conference. So first, these cover the talk, 2 minutes is the wrap-up session, and then 5 minutes is the question and answer. So in that, welcome all the Professor J.C. Mishi from IIT Gandhinagar. So she will give a talk on design and analysis in memory computing architecture for machine learning application. So she is currently faculty at electrical engineering at IIT Gandhinagar. She has been associated with IIT Gandhinagar almost more than 13 years. She received PhD from IIT Bombay and Masters and Bachelors from Baroda Gujarat University. Her research interest in the area in memory computing and machine learning application, hardware accelerator for ML, approximate computing, radiation hardened design for this application, asynchronous logic. She is recipient of Visweswara Young Faculty Research Award from METI and Excellence Teaching Award from IIT Gandhinagar. She served as a TPC member in various conferences. So kindly please, Professor J.C., please take the dais.
Good afternoon, everyone, and welcome to this talk. It's a pleasure for me to present this as in this track. I'm going to talk about in-memory computing, and in this presentation, I'll give an overview of what we are doing at IIT Gandhinagar. I'll keep it very brief to keep the time. So we all have heard several talks on machine learning. I think everyone knows that it is a way forward, and people are looking into AI, ML, and the many different solutions that one can think of, and industries. So just to give a very brief overview of why do we need in-memory computing for people who have generally looked at only the von Neumann architecture. So this graph over here, okay, this graph basically shows how expensive it is to do float point multiplication, and why do we need to look for other solutions. Why in-memory computing? Because you could do the compute within the memory. This is a very celebrated paper, Neural Cache, and it shows how when we bring the compute inside memory, you can do a large number of computations, as you can see the number. And that is one of the biggest motivation why we want to do compute inside the memory, rather than taking data out of the memory and doing compute outside. So there are two ways in which people have addressed this problem, and I think there are many more ways that we will see in the future. But largely two ways: the digital in-memory computing and the analog in-memory computing. Just to give a brief, why do we see this difference? For digital in-memory computing, you would normally turn on 2 word lines, take 2 operands, let's say, at a given time, and perform an operation on that, on those. When you look at analog in-memory computing, you would take 4, 8, 16, 32, 128 bits at the same time and then compute them together. And so there is a difference in which data is accessed from the memory in the two cases. So there are a couple of cons in both the digital and analog in memory computing. This is not the exhaustive list. But one important differentiating factor and also the memory computing would be the precision. And you can go from 8 to 16 to 32-bit precision, which is right now limited in analog. And why would one want to go for analog in memory computing, which is also used even for non-60 SRAM, 80 SRAM, even for other SRAM, other devices, is mainly due to energy efficiency. So that is the reason why analog is preferred. And so we really do not know who is the clear winner going to be. What I'm going to do is I'm going to go through a couple of works that we have done at IIT Gandhinagar in this area. So we are interested in taking a neural network and mapping it onto an analog in-memory compute unit or a digital in-memory compute unit. And these are a couple of works that have been published. The main problem that we are targeting is to make a solution that is practically feasible. That's the main goal of our research. And so we have not digressed from 60 SRAM cell. We have not gone to 80. We have not added any additional transistors. We want to make the 60 solution work. And it should work under all conditions, all process variations. And in the near future, we'll also be able to take care of temperature and voltage. So we have single bit multiplication and the main problem that we see in this single bit multiplication is the effect of process variation, which affects the data. So let's just study a few graphs quickly. So we all know how data is stored in the memory. Generally, you would store the inputs in the bit form in the memory, and you would use some form of analog, input to the bit line or the word line, depending on the different techniques. Now, you're basically multiplying weight and input. That's what you're doing. And based on the circuit that you have, we see that there is non-linearity depending on the size of your SRAM. And it keeps on varying, with all the different parameters. Now, this is a big problem, because the moment you want to implement it, you have to worry about the analog to digital converter, which has to convert this into digital. And so we want something that is going to be absolutely linear as possible, and we should have a high dynamic range that would then be made available to the ADC so that the ADC can efficiently work. That's the main goal. So when we do multi-bit multiplication, so I think there was an author who presented 4-bit cross 4-bit multiplication. When we go to multi-bit, this issue becomes even more difficult to handle. And what we have seen is you need a very large capacitance if you have to maintain linearity. And this is only made worse with process variation. So what is a practical solution? So we have a proposal. What we have done is, so we have proposed a solution where we are using capacitive multiplier to get to that large cap that we actually need so that we can do efficient conversion into a linear output. And this circuit is also using a technique called word line underdrive. This is an important thing to note. Whenever we turn on multiple word lines, we will have a problem of compute disturb. That means one cell disturbing the other cell. And so practically, if you have to make sure that cells are not disturbed before the compute, you must make sure that you either underdrive the word line or you apply some other technique to take care of it. So in this case, we have done word line underdrive. And you can see that after this technique is applied, the graphs are very linear. And obviously, we have done a lot of process variation studies. In the interest of time, I'm not going to go through all the details. But with all of these, we have an excellent bitwise energy, as we can see here, as compared to the existing designs. Sorry. Yeah. So compared to the existing designs. So this is the analog in memory computing work that we have done. Now coming to digital in memory computing work. So there are numerous solutions in digital IMC work in this domain. So one of the questions that arises is how are we going to take a neural network and we're going to map it into an IMC hardware? How are we going to do that? So in that context, we have, first what we have done in our institute is we have designed a complete memory subsystem. So a system which has the memory, all the relevant peripherals, decoders, sense amplifiers. We have the complete compute logic. This is a 128 cross 128 array, and it is easily extendable to 256 cross 256 or even more size. We have also made a memory compiler, which is an in-house memory compiler, which will do the job. And once we have this, the next question is now how do we port let's say ML algorithm on IMC, because there is a gap, right? Because you have an application, here is the hardware, how are you going to map it? How are you going to port it? So there are some works which people have done earlier using other devices. What we have done is we have come up with, we have come up with a couple of solutions here. So what we are going to do is we are first going to make a tool which will help us to take a machine learning algorithm and port it onto a hardware. We'll call it FastMem, and an extended version of that, we'll call it as IMC simulator. So FastMem is first of all a tool that helps us to compare the results that we would get on Cadence, which is a spice simulator, with this tool, so that we get exactly the same results. So we're able to match all the circuit results with the emulator results. And then we are going to apply what we call as bit serial and bit parallel compute on it. And then we will analyze the designs. So this is the arrangement. So we can take a very large array. As you will see in the next couple of slides, the different large arrays that we can take. The reason why we want to come up with a tool is because it is going to be much faster to analyze when we do analysis with multiple neural networks. So this is just comparisons with the, so OpenRAM is a tool that we have used, which is a memory compiler, and all of these results are Cadence results. So the graphs in green are the SPICE simulation results, and you can see a good match with the simulator that we are porting, which is a cacti simulator. So once we have made this first set of the tools, so we have matched all the cacti parameters. Cacti is a cache simulator with the OpenRAM, which is a SPICE simulator. Now we can do all sorts of analysis to first see how should we make a memory. So you can see here that when we make square arrays, 1024 cross 1024, or let's say 256 cross 128 or 128 cross 250, you can see that the performance is best. So that's the first input that we get from our first analysis, and it was done across multiple technology nodes. And once we have this for, the reason this graph is shown is that the tool is, will allow us to simulate over multiple technology nodes. So we have done it over different technology nodes. And then we can do performance analysis. So this graph actually shows how much power, how much energy, how much latency are we going to give to different parts of the memory subsystem. This is important because that will help us to focus our attention on the right things that we need to optimize. And then once we have the tool ready, now we have two options to do some, computation in digital domain. In analog domain, we have already seen how computations are done. In digital domain, computations are done either serially or in parallel. These are the two options. The moment neural cache paper was proposed, most of the publications or most of the works for bit serial most of the work on digital IMC were bit serial. The reason being that the transpose data was stored in the memory, and then you could do, all the columns could be used to sort of compute together. And so it was expected to be very high performance efficient. And so it makes sense to compare, bit serial and bit parallel and see really which is going to work how. So we have taken, the memory subsystem, and this subsystem we have then modeled it into the simulator, which we call it as IMC Cacti, which is built on this Cacti simulator. And here are some results that I'm going to present. So you can see that the data is stored differently in bit parallel and bit serial. This is a bit serial architecture. I'll not go into the details of bit serial architecture. If someone has any doubts on this, we'll take it at the end of the talk. Okay, so once we have decided the configurations, and you can take lots of different configurations, and then we decide the application. So here we have taken an example of ImageNet image size. 469 cross 387, and we can take multiple operand widths. So we can do it over 8, 16, 32, 64. In this presentation, I'm showing 2 of them as example, and we are doing convolution operation. So, and then we have, choices of filters also that we can apply. Now, these are some of the interesting takeaways from this graph. First of all, we can very easily tweak the tool to change the filter size, the bit width, the operand width, the memory size, the way the memory is organized. All of these parameters are programmable, as in you can change them. And then we can see the difference in the performance. What I'm showing here is the dynamic energy and the delay. And we can see that the bit serial versus bit parallel comparison here, and why bit serial is preferred, right, over bit parallel. The main reason being the performance, right? But the two have opposing nature. And so there is a sweet spot when we talk about the energy delay product. Also, one other observation that we will make is coming from the when we change the configuration, which is when it becomes more square or when it becomes larger, how the pattern will reverse. Okay, so, and then we have the dependence on the operand width. So as you can see here, based on the operand width, again the configurations will show differing behaviors. A large gap you can observe. So BPA is more energy efficient for larger operands. This will help us to understand the exact figure. So as you can see here, for the different operand widths, there is good amount of energy delay product variation that we can see. So this, okay. So the last column basically captures how the BPA, that means a bit parallel, compares with the bit serial. Okay, and we can see that there is a good amount of improvement that we observe when the array size becomes larger. So these configurations are for larger array size and for larger bit widths. Okay, this is just showing the breakup. Okay, and these are again different configurations that we have taken with different sub-banks and multiple operations. The reason why this slide is here is to help us understand that we can take multiple configurations and we can take different sub-array sizes and we can do the performance analysis. Okay, once we have this, this is the full tool. So we will have all of these as user inputs. We will have this as the main simulator that we are designing. And its output is going to be, of course, energy, power, timing, area. And we can come up with our own figure of merit that we wish to put. Accuracy is, of course, the important parameter that we want to analyze. So this is the tool which is almost complete now in our lab, and we will now be porting more neural networks on it. This is the final work that I want to show, which is on word line shaping. Now in this, sorry for the typo. So in this work, what we are again analyzing is another practical issue, which is what happens when you are dealing with a large array. So when you deal with a large array and when you have to send a signal from, let's say, a column that is very closely sitting with the decoder to a column which is at a wide end, at the end, what happens to the word line shape, what happens to it? Why word line shape is important for in-memory computing is because you are going to use multiple rows which are going to be turned on simultaneously. And so the word line shaping is very important in both digital and analog IMC. So we are going to focus on peripherals as one of the other practical concerns to make IMC a viable practical solution. Okay, so what happens is, as we can see from this figure, that when the word line travels, it is going to degrade in its shape. And so the final column is going to look at a degraded word line. This is the graph which shows how it degrades for 128 cross 256 array. And we can also see as the number of columns increase, how the slew keeps on increasing. That means it becomes worse. Okay, so what are the techniques to reduce this word line degrading? So one of the simplest method that intuitively a designer can think is just take the full array and divide it into two and put your decoder in the middle, right? So that just reduces the length by half, right? That gives you the direct benefit by square law, right? And that is one method. People have also used, to reduce the load on the word line, they have also segregated the left and the right word line drive. So you have two of these, but we are not willing to do this, so we are going to keep them together in this work. So what we'll see is, there are a couple of techniques that are proposed in the literature. So one of the techniques, which is the second technique, which is what I want to focus on in this presentation, is where you take the entire column width and you divide it in two. You can also divide it into more than two, but in this example, two, and then you would put a buffer in between. So this is the technique that we will focus on, and we'll see that it has really more benefits for digital and analog in memory computing. And these are a couple of other techniques where the buffer is kept at the end and then fed from the other end. And then there is a self-timed word line shaping technique also. So here the green graph is the one which is a technique which I just discussed. And we can see that it has perfect shape even when your word line pulse keeps on reducing. So all of these results are obtained after doing post-layout simulation. So none of these results are pre-layout because you cannot observe the word line degradation in pre-layout simulation. So the entire 128 cross 256 memory array is designed, laid out, and then we have a word line that runs in this entire column, and then we have found out the results. So all of these are post-layout simulation results. This work is also published earlier. This is the important slide, because here we see the performance benefit. The compute delay, which has a lot of improvement, as you can see, for WLS2. So that's the technique I was talking about, where you have minimized delay. And you have one more interesting thing that we will observe. So this is for analog in memory computing. Now in analog in memory computing, what we expect is that when word lines are turned on and bit line starts to discharge, our expectation is that the first column and the last column should discharge with at the same value, if the values are same. That's our expectation, which means that the red dotted graph is our expected behavior. So all the rest of the graphs are deviations from the expected behavior. And you can see that the green graph, which is our WLS2 technique, is the one which is closest. And so that is the technique that we are using in our solution. So after doing all of this, we summarize and conclude that there are many practical problems facing digital and analog in memory computing. Process variations is one of the main killers of analog in memory computing, and peripheral design and many other such questions are facing the digital in memory computing designs. And so that is the thing that we are focusing on. Peripheral design is an important thing. How are we going to design decoders which are efficient, which can turn on multiple word lines at the same time? It's a question that is not yet answered. And then a big question, tool chain. How are we going to take neural networks, machine learning workloads, port it on in-memory compute, and show which one is doing better than the other? So that's another important question that needs to be answered. So we are addressing all of these. Not all of them have been addressed, but we are on the path. Finally, I want to, so for some reason it doesn't like it. Okay, so I was just showing a diagram of the chip tape out that we have just recently completed on 65 nanometer. And it contains several modules of in-memory compute with all sorts of different compute circuits. And once we have the results, we will be able to share it with the community. Here are all the students who are involved in this project. And I also collaborate with universities and industry. And I'm also very grateful to all the funding agencies from where the support for this project has been received. So with that, thank you very much.
Thank you, Professor Joyce, for the wonderful talk. Floor is open for Q&A.
Let's say A and B. So let's say you are storing B in the memory cell, SRAM cell.
Yes.
Where are you providing the A? That's I wanted to understand.
So if you are doing digital in memory compute, you are going to store both A and B in the memory, if it is digital.
Yes.
If it is analog, there are two options. One is you store one of the operands in the memory. The other operand could be given either through the bit line, or it can be, the word line. Or in our case, what we have done is we have given the pulse widths for MS bit and LSB, which are in the ratio of 1:2:4:8, so that it maintains its magnitude properly. And then we are applying a DAC unit, which will take a 4-bit input, convert it into an analog output, and that analog output is given to a switch, which multiplies the bit line voltage. The bit line will discharge based on the value which is stored, right? And then we multiply it with the DAC. So the DAC converts a 4-bit value into an analog value. So it's an analog multiplication that happens. Once you've done the analog multiplication, you can do the addition operation using capacitors, and then you would put an ADC to convert it back into digital. That's a full flow.
Okay, so in the case where we are supplying that B through the word line,
yes.
Then in that case, in order to store A, how are you supplying that addresses? So the word line is used for addressing, right?
The word line is used for?
To store the data.
So you would, suppose you want to give a 0. So word line is going to select the word, okay, so you have a decoder which takes the address. So that tells us whether the word line, which word line has to be turned on. Okay, whether the word line is turned on or not, that is decided based on the bit value. If the bit value is 0, you would not turn it on. If it is 1, you would turn it on. And that's why that technique is not preferred, because the decoder design becomes extremely complex, and we have seen it is not practically feasible. So the feasible solution is where the decoder supplies always fixed pulse width with fixed pulse width. Okay, pulses with fixed pulse width. Got it? So if you are having a certain pulse width for MS bit, you want to generate that. And then whether it's a 0 or 1, it will still be generated. And then you would use a DAC unit to do the part which you are saying, whether it is 1, 0, yeah. It's a practical problem. And so we don't want to change the decoder because the design becomes very complex.
And one more thing,
yes.
Like, for example, in each of the columns,
yes.
Let's say you are using one DAC. So IMC is used usually for the low power operation, right? But DACs are consuming huge power.
Absolutely.
So is it compensating that power?
No, it is not. It is a research area in our lab also just now. ADCs and DACs are the most energy consuming components on the analog IMC. So we are targeting that problem. Maybe in the next VLSI we'll show something.
Institute of Information Technology. His thrust area is memory design, in-memory computation. He works
So thank you, Professor Joyce. I will go through a brief description of the IMC, then I will go for the common mode insensitive sense amplifier that we have proposed in this paper. Okay, today's agenda of presentation is, first I will cover the overview, and then the problem statement, and the IMC architecture, then the previous comparators, that is conventional comparators, then the proposed comparator, results, finding, and thereafter comparison and conclusion of this paper. So as we know that the machine learning application requires huge amount of data movement from memory to the compute unit and vice versa. Therefore, these data movements become bottleneck in terms of energy efficiency and also in terms of latency. So in one of the paper reference at the bottom, it's a Google paper. In this paper, one thing is mentioned that while even scrolling the Google Doc page from one page to the next page, 70% of the energy is going into the interconnects for moving data from memory to the compute unit and vice versa. So for the machine learning application, we have huge amount of data movement. So this data movement become bottleneck for the resource limited applications like edge devices. So we have to optimize this data movement. So in-memory compute will reduce the data movement significantly by performing the data with computation within the memory or close to the memory. So the problem statement is that, as the Professor Joyce explained, we have two types of architecture, the digital architecture and the analog architecture. So my focus of this paper is completely towards the analog architecture. So in the analog architecture, we have a analog voltage developed on the bit line. That analog voltage needs to be sensed accurately throughout its discharge. For example, if its value is close to the VDD, and it may be possible that its value is close to VDD by 2 or lower than VDD by 2. The sense amplifier or the comparator that we are using for it should have constant offset throughout from at VDD as well as VDD by 2 or lower voltages. So in this paper, I'm going to compare my proposed sense amplifier with the conventional sense amplifier with various figure of merits. So this is a typical IMC architecture. So this is the architecture that I have developed, where I have used a SRAM. This is a row decoder. This is a modified row decoder that I have used to provide the feature vector. And this is a memory I/O, and at the other end, I have used the IMC I/O and the IMC controller as well. So the main purpose of showing this one is the figure 3, where you can see that the read bit line that I have used to get the in-memory compute data, you can see it is discharging from VDD till VDD by 2. So that's why that's the main motivation of designing the sense amplifier, so that this data can accurately be sensed at the output. So this is the conventional sense amplifier. So everybody know it well. So this is the switch, PMOS switch, connected to the bit line and bit line bar. When the SAE is 0, the BL and BLB is connected to SAT and SAF node, and all the data is transferred to the SAT and SAF node. As soon as SAE goes high, whichever node is lower out of SAT and SAT, it goes to 0, and other node will remain at 1. So this is the operation of this sense amplifier. Or this is a strong arm sense amplifier, in which whichever the arm is stronger, which pull down the internal node SAT and SAF to 0, and other node will remain at. We have modified the voltage latch type sense amplifier, in which we have disconnected the VDD from the latch, and also we have used the transmission gate. Transmission gate is used for the case when either SAT and SAF is 1, and it needs to discharge to the bit line voltage. So that's why it may be possible that sometimes it needs to discharge below the VT of the PMOS transistor, and it may cause inherent offset of the sense amplifier. So these changes are made, and in the next slide I will compare the result that we have obtained for all these 3 sense amplifiers. So this is the offset result. We have done next slide. We have done the Monte Carlo simulation to obtain the offset of the sense amplifier. We have obtained the mean and sigma. This is one reference how we are calculating the offset. This is done at 0.4 volt of bit line, and BL and BLB 0.4 volt common mode value, and the sigma that we have got at this value is 6.5 millivolt, and the mean is 0.3 millivolt. And this is the offset that we have obtained for our sense amplifier. The offset remains constant throughout from 0.9 to 0.4 volt. Otherwise, however, for other sense amplifier, the offset at the lower voltage goes high, which leads to inaccurate data at the out. This is required because analog IMC itself is loss of process variability coming on the bit line. If we don't have a sense amplifier which is accurate to detect data at the lower voltages, then already we are losing lots of things from the bit line. We would have lost data here as well, and at the end accuracy will get compromised. This is the delay product. So though the main purpose of designing this sense amplifier is to keep the offset constant throughout, we have also got the power consumption for these two. The power consumption for our sense amplifier also remains constant throughout, though it is higher. Though it is higher because of the fact that we have delay is higher. Delay is higher because of the fact that we have disconnected the VDD from the latches. It is in the floating state. That's why the delay is higher compared to and the power as well. The power consumption for sense amplifier, proposed sense amplifier, coming out to be constant. This is the proposed metric alpha, in which we have multiplied power, delay, and of the offset, and we have got the constant metric throughout the common mode volt. So this is the comparison table. What I have discussed so far, I have summarizes in this table. Only the area of my proposed sense amplifier is a bit higher compared to 2 or 3 micron higher compared to strong arm and the conventional latch type sense amplifier. So coming to the conclusion, so in this work, as I already discussed, the proposed sense amplifier whose offset is constant throughout the common mode voltage, and also power consumption and a delay of the proposed sense amplifier comes out to be the constant. The proposed metric alpha is constant throughout for the sense amplifier, which is common mode insensitive.
Thank you. Thank you for the presentation. My question is, what you have done is instead of having pass gate, right, you are using transmission gate.
Yeah.
So I just wanted to understand, right, why it is reducing the offset of the sense amplifier.
Reducing the offset, making the offset constant.
Okay, making the offset constant.
Yeah, it is because of the fact that as the VDD is disconnected, PMOS also get into the play when the internal node is not close to the VDD. In the conventional sense amplifier, when the internal node is close to VDD, PMOS is just placed there to make the transistor, to pull the transistor to the VDD. For most part of the operation, PMOS remains off. But when we disconnect the VDD and the SAT and SAP get discharged below, not close to the VDD, PMOS is also came into the picture. So if you resize the PMOS transistor, what will happen? The value when closer to VDD will take care by the bottom in MOS transistor, and when the voltage is lesser than VDD, close to the VDD by 2, also it will be taken care by the PMOSs at the top. So that's the changes in the design sizes as well that decide the offset constant throughout.
Okay, so I have one more question. So there are two ways by which we provide the bitline input to the sense amplifier. One, just like you have provided in the drain of the NMOS transistor. The other way is you put an extra NMOS, right, and where you provide in the gate. So have you tried to compare your design against that kind of sense amplifier?
No, both the first two sense amplifier is already existed. One is the strong arm where the input is provided to the gate.
Yeah.
But the problem in that sense amplifier, when you switch on the signal and if your bit line is floating, then what you will experience, there is a clock coupling. The common mode, what will happen? The signal when goes high, you will get a dip on that node. So that's why I have to design that pass transistor, and when instead of pass transistor, when you go for the transmission gate, one thing is clock fit through get reduced as well. So these two, to avoid the error, I have to make these changes.
Okay, thank you.
Simulations only on 65 ST technology.
So you are working with ST?
I have worked with the ST for my PhD. Right now I am disassociated and writing.
So you don't plan to validate on silicon this approach?
Actually earlier it was planned, but there was long story for it.
Okay.
Yeah.
So this is only a CAD level which you are
yeah, this
comparing.
is only a CAD level, yeah.
And what is the spice you used?
Spice is 65 nanometer ST technology, and the I used Eldo for the simulation.
Okay.
Yeah.
The next speaker is Ms. Lavanya. So she has involved in analog and I/O design. She completed her BE in Electronics and Communication from Karnataka University and Mixed Signal VLSI and has research interest in device reliability in high-speed designs. Outside the technical world, she has a passion for
Namaskaram, everyone. Today I will speak about supply noise and peak current reduction in high-speed output drivers. The agenda remains same as the other papers. We'll go over the introduction and the problem statement. We'll compare the existing methods and the proposed solution, compare the simulated results, and then conclude the paper. Moore's law, we now have smaller, faster, and more affordable transistors that drive our modern tools and toys. So with lower area, lower power, high speed is also an important factor that drives the technology today. This requires high-speed cores and high-speed interface signaling. I'll talk about one of the challenges in high-speed signaling. So to understand that, I'll give a brief introduction on the I/O signaling through the parasitics. Shown in the figure here is a transmitter, receiver, the communication channel, and the various parasitics. The parasitic inductance L plays a dominant factor in the power integrity of high-speed signaling. I don't know about the pointer. The red line indicates the path for the flow of the current. From the supply, through the inductor, through the transmitter, the communication channel, the current goes to the far end at the input of the receiver when the transmitter is driving a high. And the bottom path indicates the current path when driving a low. The flow of the current through the inductor develops a drop across the inductor given by L di by dt. We know this because of the characteristic of the inductance, which resists the change of sudden flow of current. So when n number of IOs connected to a common supply switch simultaneously in the same direction, the drop produced would be a multiple of n. So n L di by dt, and this we call the simultaneous switching noise, SSN for short. So the aim here is to design a high-speed I/O driver without any reliability issues. By reliability, I mean the data reliability, device reliability, metal reliability. Shown in the figure here on the left side is n number of IOs switching simultaneously in the same direction. All of them are driving a high here. And on the right is a static buffer that is driving the output high. The output has remained high. And when all of the IOs on the left side shown are switching simultaneously, that creates a drop across the inductor, which is equal to Ln di by dt, and that produces the supply dip shown there. So the output now, instead of just remaining a high, just follows the supply. This is sensed by the receiver as a low. So now that is false data. All this jitter, crosstalk, or oscillations due to supply noise that we talk about is nothing but loss of data. So we want to prevent that. This was about the data reliability. Another issue due to high-speed switching would be higher peak currents, which can affect device reliability. There are a number of methods existing in the literature which addresses the SSN. At the system level, decoupling capacitors can be used. And now there are advanced packaging options which provide very less supply inductance. Otherwise, the number of balls and bumps can be increased to effectively reduce the inductance. Switching speed can be reduced, but that wouldn't be a preferred option, which will also reduce the SSN. Preferred option is always, of course, first at the circuit level. And staggered switching is a known method at the circuit level to reduce the SSN. In case of the staggered switching, the driver is split into multiple units. And each unit is turned on after a certain delay. This has an obvious trade-off with speed. Staggered switching also leads to higher peak currents in certain sections of the driver, which can affect the device reliability. So now coming to the proposed solution, the complete driver is turned on as a controlled current source with the initial very low overdrive that provides a lower di by dt. I'll explain the concept with respect to the P driver, and the same concept applies to the N driver with the voltages reversed as the drivers are symmetric. As the signal PU rises from low to high, transistor P2 is turned off and N2 turned on. N2 is designed to be a small transistor, and so the initial overdrive to the transistor PP is lower. So the PP comes out of cutoff into saturation with a very low overdrive, so lower current and lower di by dt. It should be noted that the P driver gate is a highly capacitive node because the I/O drivers are usually huge in size to be able to drive the high external load. And so the initial overdrive is lower, the current is also lower. So as the P driver gate discharges, the inverter INV2 turns on, which is designed to have, which has a skewed switching threshold. And so the voltage V2 rises to turn on the transistor N22. N22 is just an auxiliary transistor to N2, and so they together now start discharging the P driver gate. This continues, I mean the P driver gate starts discharging, the node V2 starts rising further, and P driver gate is further discharged. So there is a gradual but continuous change in the VGS for the P driver and a linear rise in current. This is what maintains a constant di by dt. And it should be noted all the units of the driver are simultaneously turned on, and so speed is not compromised. So in a nutshell, what we can say is this whole mechanism mimics a controlled current source, which leads to a linear rise in the current, and so we have a constant di by dt, and which gives a reduced supply noise. These are the simulated waveforms for the proposed circuit. The PU is the input signal which rises sharply, but then the blue-colored V2 voltage, it was the inverter output that rises slowly in accordance with the P driver gate voltage, fall of the P driver gate, that is the green in color. So the linear rise in the current, device current, is shown in the plot here, and the resulting supply dip. The results have been compared between the two methods, wherein the driver sizes are exactly the same loading conditions, everything remains the same except the pre-driver. So shown on the left are the P driver gates. The dotted lines showing the turn-on of the staggered switching drivers with the discrete turn-on with delay between the each stages. And in the solid green lines is the proposed driver, where all the units turn on at the same time, but with a gradual change of gate voltage. On the right are the resulting simultaneous switching noise waveforms, which have been simulated considering 4 IOs switching together. Clearly, the supply noise is very well controlled in case of the proposed circuit. Here, the peak currents meaning the switching currents in the two circuits have been compared. The values have been normalized to that of the proposed circuit. So it can be seen in the blue bar graphs, a uniform low value of peak current in the proposed circuit. The orange bar graphs indicating the peak currents in the staggered existing method. So the higher peak currents not only affect the reliability of the device, but the non-uniform distribution create ununiform aging across different devices in the driver, affecting overall lifetime of the IC. I ran through very fast so that I don't run out of time. So in conclusion, the proposed circuit achieves the reduction of SSN and peak current in high-speed IOs without compromising the speed of operation and area, at the same time improving the device reliability and lifetime of the IC. So better key performance indices have been achieved in comparison with the staggered switching method. That is 6.7% reduction in supply dip, 8% reduction in ground bounce, and 20% reduction in peak current. All of this with lower area as shown in the proposed circuit. Thank you.
Thank you. Floor is
That was a wonderful piece of circuit that you have added before the gate. My question is like, how much impact did you see in your pad slew rates? Because if it is lower because of gradual, let's say slewing in your gate input, you will see a slower or a fall time or a rise time. So what was the challenge? Because I also saw that it's only for 400 megahertz.
Yeah.
Like for maybe 4 or 5 Gbps, what would be the impact of this circuit? Is there any study on that?
This is up to 400, 500 megahertz. It's not for of the order of gigahertz. And it should be noted, there is no difference in the slew rates because, as I said, the speed is not compromised. We have achieved the same speed for the existing method as well as the proposed solution. What happened in the staggered switching or the existing method was just a part of the driver was turned on with delay. But in our case, the proposed solution, the complete driver is turned on. Though it is gradual, the complete driver is turned on, and there is continuous linear increase of current. So the speed is not compromised. We are still able to achieve the speed.
Yeah, if you have any data on the pad slew rate that or
It's
decreasing,
not.
it's almost constant, then your peak current should also have been more or less constant as well.
Here, the peak current is not depending on the load. Here, it's being charged through a controlled current source, and that's why the peak current is lower. You're controlling the current that is charging the output load.
Say input-output padding you are seeing there, and then making some constant current.
Yeah, no, it should not impact with the change of load.
Okay, and supply also, it is somehow controlling the current with change in supply voltage.
Yeah, even if we change the supply, but still throughout the driving, I mean, it would be different for supply 1, supply 2, supply 3. But still, it will be constant for that supply.
You have implemented this in 16 nanometer FinFET, so has it been tried before that as well, or it's only this techno where you have introduced? Meaning, have you implemented in 28 or 40 bulk?
No.
Okay, so this is a patented one by Intel? You have patented it?
No, this hasn't been patented.
Okay, okay. And it is only for 1.8 volt IO. Did you try with, because I assume the device is in 16 nanometer is 1.8 volt.
That's right.
Side. So if we want to have a 3v3 interface, do you have any proposals how to implement this?
That would, we would need again a different concept to be able to tolerate 3.3 volts. With just this driver.
Assuming a 1.8 volt device.
Yeah, assuming 1.8 volt device, but if I have to support 3.3 volt signaling, just this concept won't work.
That is why I am asking that normally the reference-based architecture which is used for driving it, how well we are able to adapt this technique over there. It has not been explored yet. So that is part of the patent. This is open. We have published a paper over here.
Yes.
Thank you.
Thank you.
Use the ODC cap that you use for the IO banks.
Oh, yeah, this did not need any additional decoupling capacitor. The SSN is very bad and such techniques are not present. Then we need additional decoupling capacitors, or the speed is much higher. But at this rate of speed of operation, even if other techniques needed, this technique does not need it.
Dr. Gaurav Kaushal is an assistant prof at ABV IIITM Gwalior.
Here, Gaurav Kaushal from IIITM Gwalior. Basically, this is the one of the work that we are working in this present domain, and that is the basically in the first day from 8th. We are listening that in-memory computing and all these things. So the topic is similar, near to. So this overview, problem statement, proposed solution, result, finding, conclusion, reference, and question and answers, all these things. So the starting is as we are working in this present era, in which I will just say that, say, suppose we are using the MacBook. Say in MacBook also we are using some domains in which we are using the in-memory computing. Not every part, but some part we are using. So in-memory computing, why? Because we want to increase the bandwidth, we want to reduce the latency, we want to improve the power efficiency, we want to improve this. So all these things we are getting the solution, one solution in memory computing. Okay, so in this, regarding this, I am going to present one of the 10T SRAM cell for this application. And so we have used the one virtual ground concept in this 10T transistor SRAM cell, and for reducing the power consumptions basically. And then we have fabricated the one, we have sent the one chip for fabrication, that is the 4 kV SRAM chip. And then we have used this in-memory computing architecture in that chip. And the die size which we are using is 5 × 5 mm square. And the proposed IMC architecture performs 1-bit logic as well as the, you can say, 1-bit addition operation at the 1.8 volt. And post-layer simulation, we are achieving the 60 megahertz frequency. So this is the some overview of the today's presentation. So this is the problem statement. We can see. So the von Neumann architecture, there is a problem that we want to make some cycles to data transfer from memory to ALU unit and all these things which are making it that latency is low and bandwidth is limited, and all these solutions we are achieving if we are using the in-memory memory. So we are performing the operation like Boolean operation, we can perform the arithmetic operation inside the memory. So that is the only, that is the advantage and biggest, basically, if we are performing all these things, then some challenges are still there. We will address these challenges because the challenges are more important, and we need to address those challenges when we are going to make the architecture. So this is the IMC-based problem statement is IMC-based system with conventional 60 SRAM cell have a lower noise margin due to their due to their single path. Everyone is known because there is a no read decoupled path. So the same path is using for the read and write operation, which makes there is a compromise between the read and read as well as the write noise margin. So IMC base 80, 90 base, 10T SRAM base have been reported already. Right now, we are proposing a new SRAM cell with a high RSNM, WSNM, and required, we are obtaining a good IMC operation. Okay, so this is the one just simple 10 transistor SRAM cell in which I have used the one M5 transistor, and which is using for during write operation. We perform this, we turn off this operation, say suppose turn off this transistor. And so it is somewhere increasing the write ability for performing the write one operation. Okay, and we are using the read decoupled path. So basically, in our design, basically we require the two read decoupled path. So we are using the two read decoupled path here and one write. So two read, one write operation we are performing. This is the requirement in our some companies, or you can say some requirement of the project. So that's why we have make it this architecture. So we have make this layout by using the 180 nanometer SCL technology. Okay, and so the advantage is coming only when we are performing the write one operation. We turn off this GC1, and read operation is similar when compared to other SRAM cell. Okay. And so this is the, if we see the just SRAM cell comparison, then I am observing here that we can, so this is the some read and write operation that we are performing. So here you can see the GC1 is, we are using the hold operation. We are keeping this transistor in VD. So it is in off condition. If we are performing the write one operation, then we are keeping the GC1 in the ground position. So that's why it will be in the off condition, and that's why it is reducing the also power at the same time during write one operation. And so this is the read one. Read is similar to the read decoupled 80 and 10T SRAM cell, and this is only, so the point is coming here. Then when we are making the new any SRAM cell, then are the few issues that we need to cover. One is the half select issue. Okay, the half select issue is, what is the half select issues in the SRAM architecture? So suppose the selected cell, we want to perform the read and write operation in a selected cell. But what happened if we are performing the if we are performing the write operation in the selected cell, the unselected cell may be in such a way that the data may be turned, or you can say data may be flip in the unselected cell. So if there is such a problem, then the row half selected and column half selected. So when you are talking about when we are making any SRAM cell, then we also need to consider the half select issues. So to analyze this half select issue, we need to perform the Monte Carlo simulation for the unselected cell. Okay, so we have performed the unselected cell. We have performed the Monte Carlo simulation on the unselected half cells. Okay, so this is the, you can say that we have performed this Monte Carlo simulation to analyze this whether we have any problem or not. So this architecture doesn't have any problem in such a way. Okay. So if you have any question in this half select issues, then you may ask or you may contact later also. So in this, at present we have make the complete in-memory computing architecture using the 180 nanometer technology. And in this we are using the 10T SRAM cell, decoder, ground decoder, VGND decoder, write driver decoder, pre-charge circuit, sense amplifier. And here you can say 8x1 multiplexing circuit technique is used. So what is it? It is making something like bit interleaving. Say suppose we want to transfer the 8-bit data. So that's why in that case we require that multiplexing technique. Okay. So finally we are using some sense amplifier here. Okay. So that sense amplifier is there, and then this is the complete layout of this complete you can say that chip. Or you can not chip, it is the just memory, in-memory computing architecture layout. Okay, so the another issue when we going to the in-memory Boolean logic, the another issue is coming the you can say failure, compute failure. Okay, what compute failure here we can see some performance like OR, NOR, and NAND gate. It is the logic and everyone is getting from initial, I suppose everyone know. But compute failure is also very important aspect. So what is the compute failure here? So suppose in M7, say suppose I will say that this is the upper one and the lower one. There are the two core is the one of the SRAM. Upper one is having the 1 value and lower one is the 0 value. In that case, we may see the compute failure in the conventional 60 SRAM cell architecture. Why? Because the bit line, suppose there is a 1 is stored in somewhere, but due to the discharging of the 0 value, the data may be flipped. So it will come more when we have a stronger NMOS as compared to weaker PMOS. So when we are making the in-memory computing architecture, compute failure is the one another important concern, and we need to observe all these things that whether we are possible. So that's why we switch from conventional 60 to the 8T or 10T SRAM cell, which having the the SRAM which is having the read decoupled path. Basically, read decoupled path we will perform the read operation and data cannot be switched. Okay. So this is the drawback in the conventional 60 SRAM cell. If you will perform the in-memory computing operation, then the compute failure will occur and there are a lot of chance. So to avoid the compute failure, you will definitely switch to the read decoupled SRAM. Okay, so in this IMC, we have performed the OR, NOR, and NAND logic, and I suppose many of you know that how can you perform. So here not giving this some information. So the another thing is to perform this operation, we are using the one V reference supply voltage, and to achieve the reference supply voltage, we have make this reference voltage generator, and it is reported in some papers, and we have used this circuit to require the suppose 0.9 voltage we are making. So suppose VDD is 0.9 VDD we are making by using this voltage reference circuit. So by using this and by using the sense amplifier, we are achieving the Boolean logic operation. Okay, so the Boolean logic operation, all these data is given on a single slide, but it is Okay, so this is the some arithmetic operation also we have performed. So as you can see here, that in the bottom unit that we have the sum as well as the carry unit there. So we are also performing the 1-bit addition operation by using this. So we have seen this data, that arithmetic operation. We have successfully obtained the logic operation as well as the arithmetic operation by using this logic, by using this in memory, by using this SRAM cell. And here you can see another thing, that RVLV, this is the line which is after some time it is constant. Why it is constant? Because RWL line after some time it is going to the bottom. RWL is the something like you can say making the path for you can say that RWL is indicating here. So we are not keeping it at one value and we are reducing to the 0 value. So discharging path will not be achieved, will not get. So why it is important? If you will keep continue on, then there will be continuously discharging. And in some SRAM cells, means in 80 SRAM cell which is coming, which is having the even 80 SRAM cell, they have the 2 redecoupled path. In that, sneak current is coming in the picture. So that's why to improve the efficiency, power efficiency, we need to make the circuit in such a way that this RVLV should be constant after some time. It should not be discharged continuously. Otherwise, it may create the problem in our in-memory computing operation as well. So here we have checked all these operations for all the 0, 0, 0, 0, 0, 1, all the case. Okay. So this is the, and then after it, definitely when we are performing all these operations, then SRAM performance in terms of the Monte Carlo simulation, we have analyzed it. So here you can see we are achieving the mean value is very high. It is 655 it is not 0.655. It is not 655. Okay. So this is the and also the, because it is the redecoupled path, we are achieving the very good RSNM mean value and very less you can say sigma value. But you can say here here you can say that because we are using the virtual ground concept during the write one, that's why we are getting the you can say WSNM is 1 is very high as compared to WSNM 0 value. So WSNM you can say mean value of the WSNM 1 is higher, and WSNM for 0, WSNM 0 is lower, because definitely virtual ground concept is using during write one operation only. Okay. So when after it the another concern is that we need to compare with SRAM with reported. So we have observed, we have compared with the reported conventional 10T as well as the 90 and state of the art. So we find that overall our efficiency, write energy and as well as you can say that area and you can say leakage power. So we are meeting conventional 10T as compared to 90. Okay, so somewhere if you compare it overall factor by using the quality factor, then we are achieving the very good quality factor as compared to other one. So this is a good way to make the one platform. So here is the one another thing is that we have make the one complete tape out for this. We have sent for the tape out and okay. So in this we are using the some you can say corner, padding and all these things. Here the area is indicated for the SRAM IMC architecture, not complete chip. So the SRAM area is 65%, drivers area is 34%, sense amplifier 0.4%. When we see the power consumptions, the driver consume a lot of power, 71%. We are talking about the complete IMC architecture. The power consumption in driver is very high. Sense amplifier 5.92, precharge circuit is 22.92, and the SRAM is including under the precharge. So you can see the maximum area is covered by the driver circuit. Okay, so we have achieved the frequencies 60 megahertz at 180 nanometer. Okay, so this is Okay. The another important factor is that what I can say that SRAM we are comparing, and this is the we are making the some logic energy efficiency tops. You can say trillion operation per second per watt, and we are achieving 0.43. And so we because the logic have a different and arithmetic operation require the different frequencies, so we have the different tops for different arithmetic as well as the logic. Okay, and so this we can see here, this is the comparison overall, and here also we have some advantage in terms of the okay, we have so this is the quality factor that we have. So here we have used what is the quality factor that we have used, quality factor RSNM, WSNM, HSNM, area, energy, delay and leakage. So we use this formula to make some synchronize to compare our work with the reported. And the energy of the proposed SRAM cell architecture decreased by 3.09% with respect to TCAS 18 paper and 0.14. So we have compared and we have shown these results. Okay, this is the post layout simulation result. All these results are the post layout. So this is the conclusion overall. The energy efficient NT-SRAM cell with enabled right stability is proposed is means is better as compared to when compared to the other SRAM cell. Higher RSNM, higher WSNM, and 89% lesser write energy. Okay, and 96% lower leakage power and 22.5% higher. So that is the layout in the basically the layout we are making. We need to make sure that the half select issues, there should be no problem in the half select issues. So when we are making the layout, so we should ensure even if it required a lot of metal layer, you can make it, but the half select issue problem should be avoided. So we have designed the layout and avoiding it.
How half select is related to the metal layers?
The thing is, I will say just
that metal, the square bigger metal is for some connections, is VDD or GND connection. What it is?
Which you are saying that which metal layer?
VDD is written.
Square. So I will be giving a talk on memristor based high speed and area efficient comparators in imply logic. So this will be my agenda of the talk. First, I will be giving an overview regarding our work, then by defining the problem statement, followed by the brief introduction to memristor and the imply logic. Then we will give the design of the 1-bit comparator in imply logic, followed by 2-bit comparator using 1-bit comparator. Then we will show you comparison results and simulation results and comparisons, followed by findings and conclusions. So first, I will give you a brief overview of my work. So like all the previous presentations have talked about the von Neumann bottleneck and why we need to look for other alternative computing architectures. So similar for me also, like there is a data transfer back and forth between the processor and memory, which limits the high computing performance. So what are the alternatives for that? Like we search for alternative computing technologies through emerging non-volatile devices, such as memristors. So memristors can store as well as compute the data. Then using memristors, we have designed an in-memory computing comparators. So comparators are largely used in ADCs and DFT circuits for comparison, magnitude comparison. So the proposed designs are optimized for area as well as speed and for applications in neuromorphic computing. So, so currently, what are the challenges faced by these CMOS technologies? So like we all know, like Dennert scaling has been stopped, and so Dennert scaling basically means like as we keep scaling, the power density remains constant, but that has stopped now because of as we keep going on reducing the size of the transistor, leakage currents come into effect. And similarly, so these are the challenges faced by the CMOS technology. Other are the faced by the computing architectures, which I've already discussed, like von Neumann, bottleneck. And so what are the alternatives for this? Either we look for the resistive computing or quantum computing, and through emerging devices such as memristors or spin wave devices, these are the some examples of alternate to CMOS devices. So let me start with a brief introduction to memristor. So basically, memristor simply means a register with a memory. So it remembers its previous state, like it was 0 or 1. So similarly, like we can see two states, memristor can switch between its two states, that is high resistance and low resistance. So the logic is defined by these resistance states. So if it is in high resistance, we will say it is logic 0, and if it is in low resistance, we will say it is logic 1. So in the right hand side, topmost right side, I have shown the IV characteristics of a memristor. So if we go to the, like a sine wave is applied of 2 volt in figure 1, and figure 2 shows the IV characteristics of this circuit. So if we see, like when we are increasing the voltage from 0 to 2, so at the voltage amplitude of 2, it suddenly goes to, current increases. So in this the memristor is initialized with logic 0. So as current increases, this means the resistance decreases. So we get at voltage equal to 2 volt, the memristor is set to the logical 1 state. Likewise, if we backtrace that to the from 2 to 0 or 2 to -2, then we can see at around -1 volt, it goes back to the minimum current, and which defines that our memristor goes back to the R off state, that is high resistance. So here in this, the high resistance is denoted by 300k ohm, and the on resistance is defined by 1 kilo ohm. So so these are the similarly denotes that logic 0 corresponds to 300 kilo ohm, and logic 1 corresponds to 1 kilo ohm. So from here, the two important voltages which we see are the V set and V reset. So V set is the +2 volt and V reset is -1 volt. The voltages in between these voltages is termed as V conditional voltage, which will not change the state of the memristor. So this is about the memristor. Now how to use memristor to perform the logical operations. So there are different types of methodologies available to do the design the logic. So the one which I am using is the imply logic. So what we do in imply logic, like simply means P imply Q. So it is denoted by P imply Q or P right arrow Q. So which results in a Boolean expression of, in figure 3 we have shown two memristors X, Y. So its X imply Y will result in X bar plus Y. So in figure 3 you can see there are two memristors connected with a resistor. So these X and Y stores the input as well as the output. The output is stored inside the memristor Y. So it will be stored wherever you will apply the V set voltage. So if you see like the truth table defined in table 1, for X, suppose both of the memristors are initialized to high resistance state, that is logic 0. So both, and we have applied simultaneously we applied two voltages, V condition and V set. So when we apply these voltages simultaneously, because of the high resistance of both the memristors, the voltage across the common node across RG is equivalent, is very small, that is we can consider equal around 0 volt. So if we see the voltage across memristor Y, so it will be equivalent to V set. So if the V set is voltage around memristor Y, so it will change its state to 1. So we can see when it is X0 and Y0, so it results in the operation X imply Y and Y changes its state to 1. So likewise, when X is 0 and Y is 1, memristor remains in its initialized state, that is Y is 1, because when the X is high resistance, so voltage across will not be enough to So when it is x is equal to 0, likewise the v set minus v condition will come across the memory register y. So it will not change its value. Likewise, these operation results in the p imply q, x imply y truth table. Now through this we can design different logical operations. Like you can define NOT gate, AND gate, NOR gate, NOT, NAND, like this. Every logical operation or gate can be designed through the imply logic. And this is directly compatible in a crossbar array. That is the biggest advantage of the imply. There are other methodologies like magic where you can only use NOT and NOR for implementation inside a crossbar. So for doing a NOT, I will do the x implies 0, which will result in the NOT of x. Likewise, for AND operations between x and y, you need 3 imply operations. And for OR, you need 2 imply operations. So using this, we have designed the our comparator equations. So for the design of 1-bit comparator, so we know the basic Boolean equations for magnitude greater, magnitude less, or equal. Then we did its equivalence in imply logic for like f a greater than b, which implies greater between the 2 bits. It is a imply b NOT operation. So like for a less than b, b imply a NOT operation. And for a equal operation, these are the equivalent imply operations. So you can design in different ways. So this is not like you can do with only this. You can design with different ways. So we have chosen this to give us the minimum area and the high speed. So if you see our first figure 4, this is an area efficient serial design. So it requires only 4 memory registers in serial, which can give the result of 1-bit magnitude comparison. So if now the thing is like area and speed is a trade-off between these designs. So if you want to increase the design, you will have to use more memory registers. Because the thing is like when we are using the minimum area, then we are reusing the given memory registers. So when we are reusing the given memory registers, so you need more steps to compute the output. So likewise in figure 4, we have simple 4 memory registers connected, which will give us the outputs in 13 steps. Similarly, in figure 6, if you see, so instead of 4 memory registers, we have used 6 memory registers, which result in significant reductions in step. So these are the serial topologies. In serial topologies, what we do is like we do all the operations in a single row, and there are multiple columns. So the single row, multiple columns is the easiest way and to do the computations, and also it doesn't require any modification inside a crossbar array. But it results in more number of computational steps to get the final result. So we can also design using a parallel approach. So what we do, instead of doing the serial computation one by one, we do the independent operations on independent rows. So figure 7 does the high-speed parallel design, which shows for like if we have ABX in the row 1, section 1, and ABY in section 2. So ABX and ABY from this, you can see from the equivalent imply logic, FA imply for FA greater than B, we need A imply B NOT. And for A less than B, we need B imply A NOT. So we can do these 2 operations independently on 2 rows. So this can be done in 2 steps, and followed by the equal operation because we need the results of the previous lesser and greater computations. So likewise, so these are the proposed imply operations. What are the steps? So like you see, for the first design, which is the area efficient design, we need 4 memory registers, and the total number of steps required are 13. So like you see in the step number 5, we get x is equal to FA greater than B. So we get the greater result. And in step number 8, we get the lesser result. And in step number 13, we get the final equivalent result. Similarly, if I use just 2 memory registers more, I can reduce the steps from 13 to 8 by doing the same operations in 8 steps. And finally, the 1-bit high-speed design, in just 2 steps, I can do the greater and lesser comparison, because both are independent operations, both are performed in different sections. But the result of this is needed for doing the equivalent comparison. That takes another 4 steps. So in all total, it requires 6 computational steps using 7 memristors. So using this, we have designed a 2-bit comparator using the results of 1-bit comparison. So this is the architecture of 2-bit comparator. So in figure 8, if you can see, like, we have used 4 rows. So what it is designing, it is doing the 1-bit comparison in the parallel mode. So like row 1 and row 2 consider is as for the A0, B0, that is for the lower LSB, and A1, B1 is the MSB. So these two will compute at the same time the individual bit comparison of A1 with B1 and A0 with B0. So this can be done, this I have defined in the equations, like G1 represents the greater result of A1, B1, E1 is the equivalent result of A1, B1, and G0 represents equivalent result of A0 or greater result of A0 and B0. So like these equations are then converted in the form of imply operations. So after that, we have used the 1-bit comparison results. In table 7, we shows the computational steps which are needed for the designing 2-bit comparator. So here we can see, like, steps 1 to 6 will be as same as for the 1-bit design, because those can be completed in 6 steps. We get the individual bits comparison results. Now using these independent individual bit comparison, we will design for a 2-bit comparison results. So same is shown in the step number 7 to 17, which after the 17 steps we get the final results for greater, less, and equal. So but these different rows gets connected with the help of different switches. So these switches gets on and off by during the application of these voltages. So the different operations can be performed. So these are the simulation results. So we have actually used the VT model simulation for 1-bit comparator design. So here we have shown our logic 0 is represented by the memristance of 300 kilo ohm, and logic 1 is defined by the memristance of 1 kilo ohm. So figure 9 shows the simulation results of, these are the SPICE simulation done in Cadence Virtuoso. So if we see, like, every 5 nanosecond denotes one computational step. So figure 9, you can see that X is represent in 25 nanosecond, the memristance of memristor X is at 300 kilo ohm, which denotes logical 0. Likewise, at the step number 5, we get at step number 8, we get the result of FA less than B, which is 1. So I have used 2 inputs, A is equal to 0 and B is equal to 1. I am doing the comparison between them. So this results in the output FA less than B, as the memristance goes to 1K, denoting it is logic 1. Similarly, I have done the simulation for high-speed design, where we get all these results, which functionally verifies the proposed implied steps. Likewise, these are for the 2-bit comparator design, where X0 and Y0, Z0 stores the individual bit comparisons, and then we are using these to do the final 2-bit comparison design. Like figure 11 shows the simulations of individual bits, then figure 12 shows the final 2-bit comparator design, comparator output. So what we find out from these different designs is that, like, for area efficient serial design, you will need only 4 memristors, but it will require 13 computational steps. Similarly, if you want to enhance the speed in a serial design, you will have to increase the memristors. So if going by increasing it by 2, you get speed gets reduced from 13 to 8 with an increment of 2 memristors. Also, the high-speed design gets the result computed in 6 computational steps using just 7 memristors. So likewise, then we find out that for designing and speed area optimized design, the serial approach is the best one. And for doing the high-speed computations, you have to increase the memristors. And for an optimized number, you can use a parallel design which will result in a more optimized number of speed as well as the area. So from this table, you can see for 1-bit high-speed design, it takes 6 steps and 7 memristors. And improvement in speed, it is compared with 1-bit, not with 2-bit. So you can see it is a 54% improvement as compared to the 1-bit area efficient design. And the figure of merit is calculated by taking the multiplication of number of steps required with the number of memristors. So these are the findings, like how to, there are 3, if the application is for area constraints, then we have to use a serial architecture. If you want to optimize for high speed, then you can use the parallel design. So likewise, I have presented an in-memory comparator using memristors in imply logic. So similarly, if you want to go for an area efficient design, you can look for the, it will result in less number of memristors with more number of computational steps. And just like that, I have our 1-bit comparator design just takes 4 memristor, and while a high-speed design takes 6 steps. So that's all from my side. These are my references, and thank you.
Thank you very much.
So, so I basically have I have 2 questions to ask. So the first thing is this memristor, what the results you obtain, can you compare this with some CMOS technology, and can you enhance the merits of the results?
So basically, we haven't compared with the CMOS primarily of the reason because these are both different technologies. So if I'm comparing with the CMOS, it will not be a valid comparison, because as such, memristor requires very less area as compared to the CMOS implementation of 1-bit comparator. So that's why we haven't compared with the CMOS technology, because we are providing an alternate to the CMOS device.
Yeah, when you try to provide an alternate to CMOS device, there must be some advantage.
And plus, it requires less area. Like if you see for 1-bit or 2-bit, so you can see I can do the AND operation in
making it R on, you have to apply some voltage. Turning off, you have to apply some voltage. And you also given 1 kilo ohm R on and 300. Why did you need to stick to only those values?
So these values are flexible, but we have taken these values according to the actual reported physical device. According to your own needs. So likewise, we have used the physical devices which have been reported in the literature to match the simulated results with the practical ones. So that's why we have used 300 kilo ohm. So if other device is using some 100 kilo ohm for logic 1, so you can use like that. But you have to match with that reported device.
Okay, that's all from me.
Okay. Thank you.
Hello sir, I actually have a doubt. So while you were showing about the first 1-bit comparator, you said that it needs 4 memristors for about 7 steps.
Yeah.
And
13 steps it requires.
13 steps, and if you use 6 memristors, it will be done in 8 steps.
8 steps.
But while coming to the 2-bit memristor, the complexity is being increased as we see.
Yes. Yeah.
And if we need more bit comparison, how will be the
so the area will definitely get increased. Like you can see, I need 22 memristors for 2-bit, whereas I'm doing for 1-bit in 4 memristors, if you see like that. Because then complexity gets increased as you increase the bits.
So while comparing the trade-offs, for example, like if you want to trade off between the area and the number of bits we are comparing, so until how many bits can we keep going using the memristor technology?
You can keep going up to whichever number you like.
But while comparing to MOSFET,
it will always be less than the MOSFET. If you design in a serial way and in a parallel way, so in serial way it will always be less than. So less than the area will always be optimized. It requires very less numbers. In parallel, you can get speed as well as area optimization done. It will be less than the CMOS, that for sure.
You give some touch-up points about the power comparison, baseline offset versus the proposed design.
So actually, like I haven't reported in the paper, but the power, like we do the energy consumption. So energy consumption comes in around, it depends on the logic. So like for 0, 0 it is different, 0, 1 is different. For around like for, if we take the average of all the input combinations, it comes around, I would say like 400 femtojoule we were getting. But we haven't shown the power because it is, it will get changed according to the parameters you are using.
But it is this 400 joule, it is more as compared to the classic model, or it is less?
It is less than the 400 femtojoule is less than the CMOS comparators.
Okay, good. And one more thing is, what is the cons? So this is the prospects.
So the cons is like the retention state of the memory stir is small as compared to CMOS. It can retain its state only till 10 to power 11 cycles.
Okay.
Okay. So after that, the state will drift. Suppose you give 0, 0, results in 1. So after so many writing cycles, it will not, 1 can go to 0.
So you want to say that there will be bit flips? Or,
yes.
Then you want to say that if you are in the retention for long time.
Long time, yeah.
So chances are there that we may lose the configuration.
Lose the data, yeah.
Okay.
Yes.
So any thought process to optimize that?
So that is for the, my area is not, that is for the device modeling people who will take that into account.
Sure.
Yeah.
Sure. Thank you.
Okay.